अभी Okay, good evening, everyone. Um, are you able to hear me? I don't know. Are you able to see me? Are you able to hear me?
Yes, sir.
Yes?
Yes, sir. Audible.
Yeah. Thank you. Yeah. So let's get started. A quick review of yesterday's class. Yesterday, mainly, we have introduced negative feedback in op amps. And I said that in negative feedback, the op amp tries to come to the linear region, not just the plus VSAT and minus VSAT saturation. It wants to come towards the linear region. So that can only happen when the error between the two terminals, they converge. Because if you see the characteristic, the limit of input is very, very small. If the gain of an op amp is 10 power 6, if the gain of an op amp is 10 power 6, and the maximum voltage of an op amp is say plus 12 or minus 12, then I told you in my first class, for avoiding distortion, what should be the range of V naught and the range of VD? So V naught has to lie between minus VSAT and plus VSAT, minus 12 to plus 12, right? So what should be the range of Vin? Vin has to be between minus 12 by 10 power 6 to plus 12 by 10 power 6. So you can imagine the range from minus 12 micro to plus 12 micro. So this 12 microvolt, we almost treat it as zero. So op amp, what is op amp doing is he's always amplifying the error difference between the two. So this VD is quite small where in negative feedback, and the output is between the plus VSAT and minus VSAT. So op amp, you can also call op amp as an error amplifier, because he's not amplifying the direct signal that you give, because the gain is very high. If he amplifies directly the signal input, the output will shoot to saturation. Instead, he has to create an error signal between the two terminals, which is so small that you almost say that there is virtually a short between the non-inverting and inverting. But what is VD? VD is V1 by 1 plus GH, right? Or let me mathematically prove this once again. So if the gain of the amplifier is G or A, here I'm applying V1 as the input, Vin is V1. And here you have the resistor divider, which is beta. And here there's V2, right? So what is the relationship between V2 and V1? So V2 is going to be beta times of V naught, and V naught is A by 1 plus A beta times of V1. So this tells that the V2 is V1 by 1 plus 1 by A beta. So what happens if A beta is large? If A beta is large, your V2 is almost equal to V1. If A beta is large, this is something called virtual short. A beta is large. Then what is the error signal? The error signal, which is so small, VD, is going to be V1 divided by 1 plus A beta. So please, there is no virtual short. Virtual short is only for kids, right? It's for chota bacha. It is not for you people. You are engineers. Now you know that there is a small error signal between the two terminals, right? So virtual is a very preamble thought. Initially, when you start, solving op amp problems, you start thinking that op amp brings the same potential here. No, if the same voltage is there and the difference is zero, the output have been zero, right? So there is a small error voltage between the two, with which the op amp is amplifying. So op amp is basically a error amplifier. Remember that it's an error amplifier. It's going to amplify the error difference between the two, and the error difference VD is V1 by 1 plus A beta. If A beta is large, definitely this VD is almost zero. It's not zero. It's almost zero between 12 micro. This VD range is between 12 micro, minus 12 micro to plus 12 micro. So you can imagine how small the error signal is, right? But last class I told you how do op-amp knows that it has to stay at almost the same potential here. So we have seen that table where if he's not here, we cannot debate that it has to be here. We can only say that if he's not here or any other value, he becomes restless, right? He keeps on increasing and decreasing and increasing and decreasing until he chooses V2 equal to V1 by 1 plus A beta. So where is op-amp going to stop? Op-amp is going to stop at a point where V2 is V1 by 1 plus 1 by A beta. So he goes bang, 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 bang here, chooses a point V1 by 1 plus 1 by A beta and stops there, such that the VD is V1 by 1 plus A beta, such that V0 by Vin. What is V0 by Vin? There's a new paper. New paper is not coming. Yeah. See, such that the error difference between the two is not zero, so there is no virtual short. Op-amp strictly is amplifying an error signal, right? So you can call op-amp as what amplifier? An error amplifier, right? A difference amplifier, an error amplifier. Okay. Now, first of all, what is the necessity of all this drama here? You take a high gain amplifier, you connect a voltage divider, and then decrease the gain, and then use it, right? Instead, suppose I want an amplifier of gain 10. I design an amplifier of gain 10. Why should I take an amplifier of 10 lakhs and then connect a voltage divider 9K, 1K, decrease the gain? Why should I do it? High gain amplifier, decrease it, and then use it, right? The reason is, what is the advantage of negative feedback? Advantage of negative feedback. Why we have to go for negative feedback? The reason is the open loop gain of the amplifier depends on temperature, frequency, mainly temperature, frequency, manufacturer, process variation, etc. etc. So the open loop gain, I'll tell you, if you ask me what is the worst thing in electronics, is the device itself. And what's the worst parameter? If you take BJT, what's the worst parameter? Beta. Beta, which is the what you call the current transfer function or the open loop gain of an op amp, these are the worst parameters in an amplifier. The reason is they change. I mean, beta, it will, if somebody asks you in an interview on what factors beta will change, right? Whatever comes in your mind, you just tell. That is right. Because it's so sensitive. All these open loop parameters, they're so sensitive. They change with the order of the day, right? On Monday, one value, Tuesday, one value, morning, one value, afternoon. They are not, they don't strictly follow adhere to one particular value, right? Because they are prone to, they change because of temperature, right? And you know, temperature in the order of the day, it's not the same, right? Morning one temperature, afternoon another, evening another, right? So the open loop gain of an amplifier depends on temperature, frequency, manufacturer. Of course, op amp, you see, there's so many manufacturers, right? You have Texas Instruments, you have olden days, we have Fairchild, right? National Semiconductor, now it's TI. So there are so many, Motorola. So many guys are there. So they have different process variation. So the open loop gain, if you directly use without feedback, it is changing on all these parameters. But what happens if you give negative feedback? If you give negative feedback, everything changes. The whole story changes. The open loop gain depends on this, right? With negative feedback, we desensitize with negative feedback, we desensitize the gain such that the final output depends only on passive components. Passive component. And in this case, who are passive components? These are resistors, right? So these are resistors. So the final gain is going to depend only on that voltage divider, 1K, 2K, 5K, 9K, right? It depends only on passive components. And what are these passive components? Resistors, they're stable, right? Therefore, the gain is predictable. So I told you, even before, I don't know what are the transistors inside an op amp, but the moment I connect a voltage divider, I'm saying that I'm predicting that this is the gain, right? Predictable, stable, and accurate. Predictable, stable, and accurate, right? So the open loop gain of the amplifier depends on temperature, frequency, manufacturer, process variation. But with negative feedback, we totally desensitize the gain such that the final output depends only on passive components. So you can tailor the gain that you want just by changing the resistor values, right? Just by having R1 by R2 plus R1, the voltage divider. With that factor, you can get a gain of 1 plus R2 by R1, right? 1 plus R2 by R1 or 1 plus RF by R1. The gain you can get just by adjusting the values of what? Resistors. Now, just tell me, necessity, why all this story? Because necessity is the mother of invention. Am I right? Necessity, so there should be some need. Otherwise, we will not do all this, right? So what is the necessity? There's a guy called Stephen Harold Black, right? He designed an amplifier, but the problem with that amplifier is it'll give a new, this amplifier was designed even before the invention of BJT. So before the invention of BJT, you know what were those devices, right? We have studied those devices, right? We had few chapters on those devices. They're called vacuum tubes. They are called what tubes? Vacuum tubes, and there's a heater inside. right? So the vacuum tube is bulky, power thirsty, a lot of noise, right? Now, with this vacuum tube, the old radios, if you remember your grandfather's radio, the old radio, right? There's a needle going on from everywhere to everywhere, boing, like that, right? So there's a big, first sound will come, for a lot of noise, and then only the voice will come, right? The moment you switch on, you have to keep tuning, if you remember, right? Those old radios have vacuum tubes in them. Then came the transistor version, which is the smaller version of the radio. And the transistor had such an impact that the radio itself is called as a transistor. I still remember in my village, right? When somebody carries the radio, we used to call he has a transistor, right? So that's a huge impact transistors have created. So this old, these vacuum tubes, with the help of vacuum tubes, he has designed a nice amplifier, right? But what is the problem with that amplifier is, any day he operates that amplifier, it will give a new output. So you just imagine you are Stephen Black, right? You have designed a nice amplifier. Morning, one output will come. Afternoon, full sound will come. Evening, no sound will be there. On Monday, one sound. Evening, right? On Tuesday, on your birthday, right? So the values will keep changing and changing because these active devices are temperature sensitive. So this man was much worried. He felt, okay, my amplifier is there, but what's the point? There is not giving a stable output. Any day I operate, it will give a new output, right? And this man, it seems he has to cross a river to go to his office every day, right? He used to row a boat. One day while rowing a boat, he kept on thinking, right? What should I do? My amplifier is not stable. Every day it is giving new output, right? Suddenly he got an idea that maybe, right, the simple mathematics he would have probably done, right? So you have an amplifier with a gain G, right? So you give an input, you have an output. You give an input, you have an output, and your V naught is G times of V. Now he felt, what if I connect one more H here? One more H, which is resistors. Now what will happen? Now what is the gain? V naught by V in is going to be G by 1 plus GH. Or in analog, we used to call this as A and this as beta. So it is A by 1 plus A beta. Now, if you keep staring at this equation, right, you just keep on staring at this equation, A by 1 plus A beta. What happens if A beta is much, much greater than 1? If A beta is far greater than 1, this is approximately going to A by A beta. And A gets cancelled. The gain will depend only on resistors. He felt, wow, I mean, this is cool, right? The whole amplifier now, the whole structure of output now has desensitized the forward transfer parameter. The forward transfer parameter is G or A, so this value has been desensitized. Now just tell me, if I design an op-amp or a BJT circuit with negative feedback, what happens if this G becomes 2G or if this A becomes 2A? Morning it is A, afternoon it is 2A, evening say it is 3A. The gain kept on changing. So naturally, when the gain changes, the performance of the amplifier will also change. Now, with negative feedback, what will happen? With negative feedback, it is A by 1 plus A beta, 2A by 1 plus 2A into beta, 3A by 1 plus 3A into beta. Now, if A beta is much greater than 1, 2A into beta is also much greater than 1, right? The A value is very large. I told you 40 dB more than your requirement, 100 times more. So this is a very big number when compared to A. So this is approximately A by A beta. This is 2A by 2A into beta. This is 3A by 3A into beta. Now what will happen in the first case? A gets cancelled, the gain is 1 by beta. Second case, 2A cancel 1 by beta. Third case, that means even if Stephen Black, after designing a negative feedback amplifier, if Stephen Black brings a new amplifier designed by his friend Joe or whomsoever, and he puts that also, the performance will be same. Forget about the amplifier. Even if you bring a new amplifier and connect with which has 2G or 3G or 2A or 3A, Finally, the gain is always going to be 1 by beta, 1 by beta, 1 by beta, 1 by beta. Who is beta? Beta is resistors. The gain is now going to depend on resistors. See, this we have practically seen, in the lab. I remember we had a nice lecturer. He used to take a soldering iron, heat it, and literally put on BJT, on the op amp. So when you literally heat it, he used to show, right? See the output. You give 1 sin T, gain is 10, so you get 10 sin T. Take a soldering iron, heat it, literally put on op amp with negative feedback, then the output is like rock solid, right? So it's going to be like that because the gain is no longer dependent on G. Even if you literally heat that, it's not the temperature of the day. I am giving temperature to it, right? You just literally heat it. I mean, don't heat it more. It's gone, right? Hardly you're going to lose 5 rupees, but at least you get that concept, right? Even if the open loop transfer parameter is prone to temperature, the output is going to be rock solid. So this is the major advantage of negative feedback. And the Stephen Black was so fascinated. Then he presented a classic paper on negative feedback, right? He wrote a nice paper. The moment they saw the paper, they felt after giving feedback, gain is reducing. Just throw it. Then again he applied, sir, please. Third time, they felt that it is a real breakthrough in the field of electronics because they are simply comparing the open loop gain with the closed loop gain and saying that the gain is reducing. So that is a disadvantage in negative feedback. No, that is not a disadvantage. You know what? Third time, he clearly explained in the paper saying that I am suffering with an amplifier of some X gain, right? X gain. And this amplifier is highly nonlinear. And if the operating point is here, morning, afternoon, evening, like that, it is giving a different gain. You say its gain is, give me some value of gain. The gain is say 10, okay, 10. And he's been using this amplifier, right? And suddenly he stopped using this amplifier. He have a new idea. The new idea is to get this gain 10, he will design an amplifier which is at least 40 dB more than his requirement, at least 100 times more than this gain in dB, right? 40 dB more, 100 times more than that value. And now this amplifier, he has given negative feedback. When he gave negative feedback to get 10, this is the performance of the amplifier. The amplifier, the linearity of the amplifier is improved so well that even if the point changes, the slope is same, the M value, M is gain, right? So this V in and this V naught, the M value stands for the gain. Even if the operating point keeps on changing in the order of the day, the gain is always going to be constant. So he felt like, so this is a plan. If somebody tells you negative feedback will reduce gain, don't believe them. Just tell them this is a technique, right? This is a technique. Have some respect for negative feedback amplifier. This is a technique. What is a technique? To get gain 10, I'm taking an amplifier which is having a higher gain, and then I'm giving negative feedback. Previously, I was getting 10, but that was non-linear. There was distortion in it. There was noise, and a lot of nonsense was there in that amplifier. But now look at my new amplifier. It's a plan to get this. So what is the term you have to use? The new books, they don't say disadvantage and negative feedback. They say trading. We are trading gain. You have to say we are trading gain. To design this amplifier, you have to take a higher gain amplifier, and then you have to reduce the gain such that this new amplifier. So as a good engineer, whom you should compare this 10 with this 10, not the open loop gain with a closed loop gain, right? And say that I'm reduced. That's a plan. That's a perfect plan. Are you getting? See, on a lottery, right? So you have spent 10 rupees and you got a 1 lakh rupee worth of what you call instruments or something, right? 1 lakh rupee worth of a cell phone. You spend 10 rupees on a lottery, you get 1 lakh rupee worth of cell phone, right? Can you say that the biggest disadvantage in this lottery is I've lost 10 rupees, right? So you can't say that. It's a perfect plan. Whether the gain is 10 lakhs or 20 lakhs or 30 lakhs, the op amp is just going to be 5 rupees, right? So if you want, so what is the plan in negative feedback? If you want negative feedback, if you want the advantage of negative feedback, what you have to do? you have to take a higher gain amplifier, and then you have to reduce the gain. When you reduce the gain, you'll find that the amplifier response is so well, so linear. There is no noise in it, no distortion in it, right? So let me repeat that. Let me repeat what I have said now. See here. The open loop gain of the amplifier depends on temperature, frequency, manufacturer, process variation, and everything. So because of these characteristics, the characteristics of the device is going to be non-linear, right? But what happens after giving negative feedback? After giving negative feedback, the gain is no longer dependent on the forward parameter A. It's now going to depend only on the feedback resistors. So the gain is predictable, stable, and very accurate, right? And when I take up negative feedback amplifiers, the reason why I'm saying that it's a lottery by doing this is, it's not just linearity. There's so many advantages of negative feedback, right? So you can simply say that a non-ideal device, if somebody asks you, give me a single statement which tells that what is the advantage of negative feedback. If somebody asks you, give me a single statement which tells you in a nutshell, what is the advantage of negative feedback? You can simply say that a non-ideal device will become ideal. That's it. Because here, after giving feedback, your bandwidth will improve, your distortion will reduce, noise will reduce, linearity will improve, input resistance will improve, output resistance will improve, right? Everything. But we have to trade gain. Trade gain in the sense, first thing, I want gain 50. Increase it and then reduce it to 50. Because you want 50, right? You're not losing anything. You want 50, have a higher gain amplifier and then reduce it to 50, right? And then enjoy all the advantages which are not there in the open loop, if at all you would have designed without feedback, right? If at all you would have designed without feedback, you would not have all these, because every nonsense is there in this open loop gain. So it's almost like a complete breakthrough. The reason is, from the worst design to the best design, you will get by giving negative feedback. The moment you give feedback, that's it. Are you getting? A non-ideal device is simply going to become ideal, right? So with feedback, a non-ideal amplifier simply converts to ideal, at least close to its ideality, right? At least it is close to its ideal behavior. Okay, yeah. And then last class, I have done two types of amplifiers. What are they? One is the non-inverting amplifier, and the other one is the inverting amplifier. What is the inverting amplifier? I told you an inverting amplifier is a trans resistance amplifier. What is a trans resistance amplifier? It is a I to V converter. Am I right? I to V converter. Now, what is the use of this I to V converter, right? Instrumentation engineers, they like to use this I to V converter. How? For example, if I don't have a microammeter is costly, right? Or a milliammeter. I don't have a milliammeter or a microammeter. What is an ammeter? What is the use of an ammeter? What does an ammeter do? Ammeter, right? An ammeter is going to measure current. A voltmeter is going to measure voltage, right? An ammeter is going to measure current. A voltmeter is going to measure voltage. Now, I don't have a milliammeter with me, right? Or a microammeter with me, but I have a cheap voltmeter, 0 to 10 volts, range, an old voltmeter I'm having. But now I want the voltmeter to measure current instead of voltage. I want to measure current. So what I do is, I want to measure current from some amplifier or some device. This is the current, I. Now this current, I have to process it. The good news is op-amp is selfless. It does not take any current, right? It does not take any current. And the current is allowed to flow through a resistor, 1 kilo ohm. And here at the output, I'll put that voltmeter here, 0 to 10 volts range here, right? Now what happens if this is 1 milliampere? When 1 milliampere flows in 1 kilo ohm, nicely, this meter is going to show 1 volt here, 1 volt. If 2 milliamperes flows in 1K, it shows 2 volt. So wherever it shows 1 volt, 2 volt, 3 volt, all that you have to do is take that voltmeter, and on that, what readings are there on the when you see through the glass, the big voltmeter, the readings are 1 volt, 2 volt, 3 volt. So what you have to do is take a paper and paste it on that, right? Paste it on that. Wherever it shows 1 volt, write 1 milli. Write 1 milliampere. Wherever it shows 2 volt, write 2 milli, right? So these are the readings. Now we are going to change the readings to 1 milli, 2 milli, 3 milli, 4 milli. So now this meter has become an ammeter now, right? And what is this technique called where you change the voltage readings to the current readings? This is technically called, don't say that I've changed the readings, right? You should not say that, right? Don't say I've changed the readings. You should technically speak, right? You should say, I've done calibration, right? I have calibrated the voltmeter to measure the variations of current. So whenever the current that is coming here, because I don't have a milliammeter, I allow it to flow through a resistor, amplify it, multiply it by a number 1000, 1 kilo ohm is 1000, and then it becomes a volt, and then you can have the voltmeter to show those variations, right? So definitely when this is an I to V converter, right? It takes the current and converts it into a voltage, right? But if you say that, no, I don't want to measure the current. I want to connect a voltage in series with resistor. 1 volt with 1 ohm, right? What will happen if I connect 1 volt with 1 kilo ohm here? The same meter, if you put, this fellow is going to give you the short circuited current here, the short circuited current of this device. 1 volt divided by 1 kilo ohm, there's going to be 1 milliampere. He will show 1 milli and say that, guy, this is your short circuited current. I'm sensing your current. I've measured your current. I didn't measure your 1 volt. I didn't measure your 1 kilo ohm. I've measured your 1 milliampere, right? So the same meter is going to show 1 milliampere. It says that I have done some signal processing now. I processed your short circuited current. If at all the same voltage, 1 volt, if you connect it to 1 kilo ohm, right, and literally short here, what is the current? What is the current that's going to flow? 1 milliampere. This 1 milliampere, which is a short circuited current in this loop, that is going to be measured there, right? So remember, the inverting terminal, when you give the op-amp is actually taking the current and processing it. Whether you want current to current or current to voltage, that's different. But It takes that current. That is important. It takes that current for processing, and then you can convert it into a voltage or you can convert it into a current. So today we are going to see the other two amplifiers also, right? What are the other two amplifiers we missed? Yesterday we have done non-inverting, which is voltage amplifier. And then this is the inverting, which is the trans resistance. So we have two more amplifiers. What are the two more amplifiers? Voltage, trans resistance, current and transconductance, right? The current and transconductance we are going to see today, right? We are going to see today, right? This non-inverting and inverting amplifier we have seen. I think this is where we stopped yesterday. And what else we have done yesterday? Non-inverting, 1 plus R2 by R1, inverting, minus R2 by R1 times the Vin. And then we have done problems. Am I right? We have done problems. What are problems we have done? We have done some adder, subtractor, difference amplifier. And then I think we stopped while calculating the input resistance of the amplifier. Yes. We stopped at calculating the input resistance. So let's continue with the input resistance. Excuse me. Yeah. So let's start. Find Rn. Find Rn. Find Rn, right? Let us solve. So for this, we have to connect a test voltage Vt and find current It. Am I right? Can op-amp draw current? No, it's the same current It here. So you have a node Vx. We don't know what this node is. We call it Vx. So if this is Vt, the voltage at non-inverting is equal to voltage at inverting. So this node should also be Vt. All right. So don't change the direction of It. The other two branches, it's your wish, right? You can take some current Ix here and Iy here, right? Yeah. Now you can apply KCL. The currents that enter the node is equal to the currents that leave the node. So IT plus IX is IY, or IT equal to IY minus IX. IT equal to IY minus IX. Am I right? What is IT here? Let's eliminate the Vx first, right? What is IT? IT is going to be Vt minus Vx by 2k. What is Iy? It is Vx by 1k. And what is Ix? Ix is going to be Vt minus Vx by 4k. So Vt minus Vx by 2k is It, Iy is Vx by 1k, and Vt minus Vx. So what is Vt here? Take it common, 1 by 2k. Right? And what is Vx? One by 2k plus 1 by 4k here, Vt, and Vx is 1 by 1k. Yeah, 1 by 1k. Yeah. Now you get me what is Vx in terms of Vt. What is Vx in terms of Vt? So once you get Vx, now you tell me what is It? It is going to be Vin minus Vx by 2k. You substitute here, you get, is it Vin or Vt? It is Vt. You get Vt by It. This is the input resistance. But let me do it this orally, right? It's okay. You can apply KCL. But what is the answer you can get? Let's do it orally. Now, you can see that the voltage at non-inverting and inverting both are same, right? So what is the voltage across 2K? It is IT into 2K. So the voltage across 4K will also be IT into 2K. So this is going to be IT into 2K drop, right? So what is the current Ix? The current Ix is going to be IT into 2K by 4K, that is 0.5 IT. So here you have IT, here you have 0.5 IT. This current is going to be 1.5 IT, right? So if you orally apply KVL here, Vt equal to IT into 2K plus 1.5 IT into 1K, it's going to be 2K plus 1.5, it's 3.5. Are you getting? So after all the KCL, you're going to get 3.5K, right? I mean, you can do by KCL, just trying to do it orally here, because I know that the voltage across 2K is IT into 2K. So the voltage across 4K will also be IT into 4. Why? Because the voltage at non-inverting and inverting both are same. So Vt minus Vx, you can see non-inverting voltage is Vt here. Vt minus Vx is IT into 2K. The Vt minus Vx will also be IT into 2K. Then what is the current Ix? IT into 2K by 4K, it's 0.5 IT. So you have IT here, 0.5 IT given by the op-amp. So the 1K is going to get 1.5 IT. So if you apply Kirchhoff's law in this loop, right, it's Vt equal to, IT into 2K plus 1.5 IT into 1K. So from here, this is orally I'm doing it. So from here, Vt by It is going to be 3.5K, right? So you can do KCL here, do some algebra, and then get the same answer, right? So the answer after KCL is going to be 3.5K. Or do you want me to apply KCL and do it? Can you do this? It's all messed up here. If you want, I'll do it here. This is Vx, Vt here, Vt, 1K, 2K, 4K. Yeah, what is Vx? You can, I told you KCL, your wish. You can even apply some of the currents that leave a junction as zero. So tell me, what is KCL? It's Vx minus Vt by 4K plus Vx by 1K plus Vx minus Vt by 2K equal to 0. So it's Vx into 1 by 4K plus 1 by 1K plus 1 by 2K equal to right. So you can take 4K, the denominator. So what do you get? 1 plus 4 plus 2, 4K in the denominator. 1 plus 2, 3. So Vx is going to be 3 Vt by 7. Vx is 3 Vt by 7. Then this is It here. What is It? It is going to be Vt minus Vx, which is 3 Vt by 7 by 2K. So 7 minus 3 is 4. 4. 3 by 7. 7 minus 3 is 4. It is 4 Vt by 14. What is 14 by 4? 14 by 4. 14 by 4 is 7 by 2. 7 by 2. 7 by 2 is 3.5. Yeah. 7 by 2 is 3.5. Yes. Okay. Fine. You wish you can do whatever way you want. There I applied entering is leaving. Here some of the currents that leave a junction is 0. Your wish. Either way, your answer is not going to change, right? See, the biggest problem with online classes is, let me tell you frankly, students are so good at all this algebra. Whenever I do it on the board, right, I just wait. There'll be some students, proactive, who are just telling the answer. When they're just telling the answer, you just go and write 3.5K. But now I don't have an option, right? It's me who has to solve the algebra now. So, okay, right? Sometimes I get stuck, doesn't matter, right? And then if I get stuck, I always think, what's the other way of doing it? Can I do it by a simple Ohm's law method or something like that so that I can, somehow get the answer? Fine. Yeah, it doesn't matter, right? And you're good at algebra, so you can manage. Once you get the equation, you can just manage solving it, right? Fine. Yeah. And then yesterday we found input resistance of non-inverting and inverting amplifier. You can take a snapshot of this and just check, cross-check. Yeah. Now, what happens if I have an op-amp and the resistors are ungrounded? I told you Miller effect is usually applied to inverting amplifiers, right? For non-inverting, if there is from input to output, then it might simulate negative resistance, right? Suppose I ground the non-inverting terminal and my op-amp has a gain A, right? This is V1 and V2. This is V0. So what is V0? V0 is A times of V1 minus V2. And we know that this V1 will become V2. V1 is almost V2 only when A is infinite. Never apply virtual short when the gain is less. We have seen if the gain was 1, there was this much error, right? So one is 3 volt, the other one was 1 volt yesterday, right? And then slowly, as the gain became 10, the error was 0.5 and the gain is 1000 like that. So once it gets 1000 or 10,000 like that, the error between the two terminals almost converges to 0, right? So V0 is A times of V1 minus V2. What is V1 here? V1 is 0 and V2. So it is minus AV2. V0 is minus AV2 here, right? Now, suppose I want to find the input resistance of such an amplifier. Such an amplifier. So what does Miller effect tell you, right? Miller effect says that this, if you have a resistor between two nodes, Vx and Vy, or V2 and V0, then it can be split into two impedances. Do you remember Miller effect, right? Or if you don't remember, I'll derive it. It can be split into two impedances. This is going to be R by 1 minus Vx by Vy, which is V0 by V2. And this is going to be R by 1 minus 1 by V0 by V2. Now, all of you tell me, what is V0 by V2 here? By the way, what is V0 by V2? It is minus A, am I right? So V0 by V2 is minus A. So this is going to be R by 1 plus A. And this is going to be R by 1 plus 1 by A. R by 1 plus 1 by A. So this is called what effect? Miller effect. This is called Miller effect. So now, when can I say V1 and V2 both are same? Is almost it should behave as if the resistance between the two terminals is 0. They are virtually a short. When is this possible? Keep substituting the values of A, you will know it. Keep substituting the values of A. The input resistance of this amplifier is R by 1 plus A, right? If A is 1, the gain 1, then it is going to be R by 2. If the gain is 10, it's going to be R by 11. If the gain is infinite, it is going to be 0. This is virtual short, see. So the input resistance is almost 0, then the amplifier naturally becomes current controlled at the inverting terminal, right? So at the inverting terminal, you almost say, if I ask you what is the resistance, this is 0. This is 0. This resistance is 0, right? It is 0 if A is infinite. This resistance is 0 if A is infinite, right? Okay, if you want a proof for it, somebody who has not attended Miller's theorems class, for him, let us prove it. Let us prove it. This is V2, V0, and what is V0 by V2? Minus A, right? Okay. Now let's prove Miller's theorem now for op-amp. Let's connect a test voltage here. What is this? Yeah. Let us connect a test voltage here, VT, and find IT. Can op-amp draw current? No, this is IT. Now, let us prove it is R by 1 plus A. So what is IT? IT is going to be V2 minus V0 by R. V2 is VT minus V0. What is V0? V0 is minus AV2. So what is minus V0? It is AV2. AV2 or AVT. VT plus AVT. Right. This by R. From here, what is VT by IT? It is R by 1 plus A. So the input resistance of the op-amp through the inverting, through the non-inverting, we know that through the non-inverting, we know it's infinite. We have already done. But through the inverting, there is virtual short. Why did I derive this? Do not apply virtual short if the examiner says that A is 1 or 10. You can apply virtual short only when A is infinite. So the amplifier is a perfectly current controlled amplifier only when the gain is very high. So just like that, I mean, now I'm clearly making a statement. Plus terminal is for voltage, high input resistance. Minus terminal is for current, but not all the time. Minus terminal is for current only when A is large. Only when A is, because when A is large, that is when the resistance becomes almost zero, the amplifier becomes current controlled, virtually zero, right? So this is a very peculiar device. Through non-inverting, you have high resistance, and through inverting, you have very, very low resistance. So it's R by 1 plus A. This is Miller's theorem, right? Oh. Yeah, I forgot. I think there's one student who said during the question answer session, he was telling, sir, can negative resistance be possible, right? So how do you get negative resistance? Yeah, this problem we will do. One more problem. Find RL. Find RL. Yeah, one more gate problem. Gate problem. The examiner said, find tau. Find tau. This for 2 marks. Normal procedure you can do applying Kirchhoff's laws, equivalent model of an op-amp. But with our Miller's, just by looking at the amplifier, you can tell this for 2 marks. The examiner has given 1000 here, 1000. The capacitor C. Here. So this is a gate problem for 2 marks. Very good, very good. Some of you have given the answers. So we have R here. R here. And what is the input resistance seen from here? Here. Suppose this is Rx. What's Rx there? We have seen that this value Rx is going to be R divided by 1 plus A, right? Is R divided by 1 plus 3, which is R by 4, right? R by 4. So R by 4 parallel with R. So if 2 resistors are in parallel, what is the equivalent resistance? It is R1 R2 by R1 plus R2, right? Or what is R parallel with R? R by 2. R parallel with R parallel with R, R by 3. R parallel with R parallel with R parallel with R, R by 4. And then parallel with R, it's going to be R by 5, naturally, right? So what's the input resistance Rin? It's going to be R in series with R by 5. So now Rin is going to be R plus R by 5. How much is this? 5 plus 1, so that's 6R by 5, right? Very good. Very good, very good. And if at all you want to find the output resistance, then you can have here one more resistor, which is R divided by 1 plus 1 by A, which is not needed while calculating the input resistance. See, the syllabus I have broadly classified only as 4 parts, only 4 parts. One is op-amp, diode, BJT, MOSFET, that's it, right? So there's only 4, op-amp, diode, BJT, MOSFET. First we'll do op-amp and a little diode and then combine both of them and then do nonlinear applications. Once we finish nonlinear applications, we go for positive feedback, Schmitt trigger. After finishing Schmitt trigger, we'll come for BJT and MOSFET side by side. BJT DC analysis over, then MOSFET DC analysis. BJT AC analysis, CB, CECC, then MOSFET, CSC. Because you can see that both answers are same. MOSFET answers and BJT answers, they're almost same when you look at the small signal model. So when you do side by side, you almost feel that you're doing only one topic, the same topic. So it's much easier for a student to analyze. Okay. Now find the input resistance of the op-amp, right? Before calculating input resistance, did I tell you that if I have an amplifier of gain 2 and then I connect a resistor between input and output, R, right? So this is V1 and this is V2. What will be the input resistance of this amplifier, Rn? This amplifier's input resistance is going to be what? It is going to be R divided by 1 minus V2 by V1. It is R divided by 1 minus 2 is going to be minus R. So this amplifier is going to simulate what resistance? Negative resistance, right? Now, if I remove R from this diagram, this is a simple non-inverting amplifier, 1 plus R2 by R1, which will give you a gain 2. So when you connect a resistor between input and output, naturally your input resistance is going to be minus R, right? Let's prove it by Kirchhoff's law, right? Let us prove it. So I'll connect a test voltage VT here, VT. According to virtual ground, the voltage at non-inverting is equal to voltage at inverting. This is VT. There is V0 here. V0 is going to be 2 times of VT. Let us prove it, right? Tell me KCL. Entering current is equal to leaving current. KCL. V0 minus VT by 1K. V0 minus VT by 1K equal to VT by 1K. So your V0 is going to be 2VT. 2VT. So now who is at higher potential? Who is at higher potential? Is VT at higher potential or 2VT is at higher potential? Is VT at higher potential or 2VT is at higher potential? 2VT. So 2VT is at higher potential VT. So the current, the actual current is flowing in the opposite. So the negative sign is taken care by Kirchhoff's law. You can see here. You can see here, I'm taking IT, the same IT flows here, op-amp draws no current. What is IT? IT is going to be VT minus V0 by R. It is VT minus 2VT by R. So it is VT by IT is going to be minus R. This is the input resistance of the amplifier. So this amplifier is going to give you or simulate negative resistance, right? So I'm going to use this block in future for building current sources. It's the Holland current source. So Holland beautifully used this circuit in future, right? What is the current drawn by an op-amp? This is entering current, this is leaving current. The current drawn by an op-amp here is 0, right? Because op-amp has high input resistance. Inherently inside an op-amp, a huge resistance. Op-amp will never draw current, right? Never, never. So this current is same as this current, and the current drawn by op-amp is 0, right? So the input resistance is going to be minus R, minus R. See, this is why I told you last class, in a day, suppose we are doing 10 or 15 problems, and the same day, please revise them, right? Just nothing wrong, just see those problems, revise them. If you don't do that, suppose you don't do it for 3 days, right? And then you end up having 50 problems. It becomes little cumbersome, right? Then and there, once you finish the class, tomorrow morning, have a cup of coffee, right? Just go through once, right? It will always be easy. And analyze them, think about them, right? You just see, the beauty is then when you don't understand the subject fully, right? The moment you read something, it should give you a chance to think. So that's the beauty actually. So when I'm saying, when I'm teaching negative feedback, some students, I really like them. They're thinking, what will happen at positive feedback? See, Are you getting? But I don't want to teach now. I will teach positive feedback only when time comes. But see, they're thinking, what will happen in positive feedback? What is happening here, right? So that should be there. It's not like just make the statement, right? Negative feedback, this positive, this. Then there's nothing, no scope for you to think, right? So we are going slowly now. We will see only what structures negative feedback. After we finish that, we will see diode circuits, combine them, do precision circuits, and then we go for positive feedback stage by stage, right? Very good. Okay, yeah, we'll do the gate problem now. So what about capacitors? If you have an amplifier whose gain is minus A and you have a capacitor C, what is C in here? C in, it is going to be C multiplied by what? 1 plus A, am I right? C multiplied by 1 plus A. So, or you want me to prove this? Right? Yeah, oh, just now I proved it, right? If you have an impedance Z here, which is 1 by SC, here I'm applying V in, this is V naught. V naught is A times of V1 minus V2. V1 is 0, V2 is V in, so it's minus A V in. And here you have I in. What is I in? I in equal to V in minus of minus plus A V in by Z. Your V in by I in is going to be Z by 1 plus A. Am I right? What if the Z is capacitor 1 by SC? So the equivalent capacitance is going to be C multiplied by 1 plus A, right? So let me solve this. I have V in R. Here I'm going to have a capacitor equivalent C multiplied by 1 plus A, which is how much? 1 plus 1000 into C, which is 1001 C, right? And what is tau? Tau is a product of R and C, so it is 1001 RC. So this is, so there were 4 options in that gate problem. If you see 10 RC, 11 RC, 101 RC, 1001 RC, 10,001 RC, right? These are 4 options given, and 1001 RC is correct, right? And all of you, please, what happens instead of 3 if the gain is infinite? If the gain is infinite, then you will have a virtual short here. Then we have seen that this resistor will become dummy, right? But now these two potentials are not same. When you can apply this is 0 and this is also 0, this is not 0 when this is 3. When is this 0? This node is 0 only when this becomes infinite. Virtual short should be applied only when gain is infinite. Are you getting? Otherwise, yesterday's class, what did we do? The same problem, if the gain is infinite, then what will be the answer, right? Problem Rn, what will be the answer, right? The gain is infinite. something you can connect, whatever you want, you can connect. This is R1 and R2 and R3 and R4 and R5 and right, a lot of things are in. Now tell me, what is the input resistance? If you can apply a test voltage VT, find current IT. By virtual ground, this is how much? 0, because the gain is infinite. Then what is IT? IT is going to be VT minus 0 by R1, and VT by IT is going to be R1. So you can apply virtual ground when only when the gain is infinite. If the gain is 2 or 3, then you have to do by Miller's theorem, right? See, any feedback structure that I'm going to draw now, you have to accept it as what feedback? Negative, because I'm teaching only negative. Even if both the feedbacks are given, it is still negative. But how do we know whether it is positive feedback or negative feedback? When both the feedbacks are given, you have to wait till I take up feedback amplifiers, right? Positive feedback. In positive feedback, I'll show you that if beta n is greater than beta p, it's negative feedback. If beta p is greater than beta n, it's positive feedback, even when both the feedbacks are given for an amplifier. Are you getting? So keep thinking, right? So you'll have doubts. What happens? Is it positive? Instead of thinking whether it's positive or negative, first accept that it is negative and see how to solve the problems, right? Because all these amplifiers are what feedback? Negative feedback. When I go for positive feedback, I'll show you, right, what is the difference between negative feedback and positive feedback, and what happens when both the feedbacks are given. How do you know whether it's negative feedback or positive? How do you calculate beta n and beta p? And then if beta n is greater than beta p, it's negative. If beta p is greater than beta n, it's positive. So we'll do that exercise, right? Because now our aim is to solve them, right? Again, you deviate and then keep checking the type of feedback. Yeah. Fine. Now, apart from input resistance, how do we calculate the output resistance? Calculate R naught, output resistance of the amplifier. Calculate R naught, which is the output resistance of the amplifier. Calculate R naught, which is the output resistance of the amplifier. Okay. So what is the procedure for finding R naught? In my introduction class, I told you what is the procedure for finding R naught. The procedure steps are: first step is open circuit load. Second step, if there is a voltage source, you have to short circuit. If there is a current source, for whenever you're finding Thevenin's equivalent, where the current source, you have to open circuit IS. Step 3, connect a test voltage VT equal to 1 volt at output terminals. Find current. Find current. By Ohm's law, find current IT. By Ohm's law, R naught equal to VT by IT, which is 1 volt by IT. So this is something I've already mentioned in the introduction, right? So let us change the setup now, right? Here I have 1K. Here you can connect VT equal to 1 volt. 1 volt, find IT. By Ohm's law, what is R naught? It is 1 by IT or 1 volt by IT. Resistance by Ohm's law is voltage by current. This is the same circuit, 2K, 3K, 1K. Yeah. Some resistor values are given, right? Okay. So according to virtual ground, the voltage at non-inverting and the voltage at inverting both are same. If this is VP, this node is also VP. If this is VP, 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 VP here also VP, right? Same node. Now here the current is entering, you can have two leaving currents, right? Leaving current. And whatever the current that flows through 3K is the same current that is flowing through 1K also, right? And the voltage at this point is 1 volt. 1 volt. So you can apply voltage division and you can directly calculate VP, or you can apply KCL. What is KCL? 1 minus VP by 3K equal to VP by 1K. So what is VP by voltage division? 1 into 1K by 3K plus 1K. It is 0.25 volt. .25 volt, right? 1 by 4. Now, let's apply KCL at this. KCL, one more KCL. The current entering is IT. The current leaving is 1 minus VP by 2K plus 1 minus VP by 3K. So IT is, VP is 0.25. So 1 minus VP is 0.75 by 2K plus 0.75 by 3K, right? And what is R naught? R naught is 1 by IT. You can please calculate this, right? Please calculate this. reciprocal of the current is already there, calculate the value, the inverse of that. 0.75 you can take out, there's 6K there, 6K, 5 times, right? 5 times, 5 into 0.75. So 6K by 5 into 0.75. I don't have a calculator. Divide 4, 24, 24 by 15. Something like that. Okay. Please do the don't believe me. Yes, this is correct. 0.75 by 2K plus 0.75 by 3K. This is correct. Just do the calculation. Okay, so 24 by 15 happens to be correct, right? This value is correct, right? So this is how we have to calculate the input and output resistance, right? An op-amp. So just recollect what we have done last class. We have done adder, subtractor, difference amplifiers. What about differentiator, integrator? Okay. Differentiator. So what was the main aim when they invented an op-amp, or when they came out with the op-amp design? What's the main idea? They wanted an IC which will do some analog computation, right? They wanted an IC which can do addition, subtraction, multiplication, division, right? Differentiation, integration, all this, some analog computation. Right? So you can do by time domain or you can do by frequency domain. You all know that frequency domain is much, much simpler than time domain, right? So first we'll do by time domain. We're not going to do this again and again in time domain, right? Yeah. Virtual, according to virtual ground, right? This is ground, this node should be at 0. There's a capacitor current IC, op-amp takes a current 0, and this is IR, right? So what is KCL? KCL is the current entering is equal to the current leaving, right? Now, what is the current flowing through the capacitor? The current flowing through the capacitor is given by C dVc of t by dt. And what is the current flowing through the resistor? 0 minus some function of time, you can take 0 minus V naught of t by R, right? But what is the voltage across the capacitor VC? What is the voltage across the capacitor VC here? VC. VC is nothing but Vn of t potential difference. The positive plate has Vn and the negative plate has 0. The positive plate has Vn and the negative plate has 0. So Vn of t minus 0, which is Vn of t. So Vc of t is nothing but Vn of t. So therefore, C dVn of t by dt equal to minus V naught of t by R. So what is V naught of t? It is going to be minus RC dVn of t by dt. dVn of t by dt, right? So this is V naught of t. So what do we understand here? The output is, I mean, if you forget the scaling factor RC, the output is proportional to the time derivative of the input voltage given. The output is proportional to the time derivative of the input voltage given. Hence, the circuit is called a differentiator. The output is proportional to the time derivative of the input voltage given. Hence, the circuit is called a differentiator. Yeah, I was telling you, what about the frequency domain? The frequency domain is much simpler. You just replace capacitor by 1 by SC. And then in Laplace, you have studied that multiplication of S in frequency domain is differentiation in time domain. Whereas 1 by S in frequency domain is integration in time domain. Am I right? Right. So let's see if this S is the multiplication, not division. If it's division, then it's integration. So it has to multiply, right? So let's see the frequency domain analysis, right? So we replace the capacitor by 1 over SC, 1 by SC is an R. Now this is an inverting amplifier. In an inverting amplifier, tell me is V naught of S, V naught of S, and V naught of S. Now tell me, this is like the inverting amplifier. What's the gain of the inverting amplifier? Minus R2 by R1. So V naught of S by V naught of S is going to be minus R2 by R1. Minus R2 by R1. That's it. So what is V naught of S by V naught of S? It's going to be minus RC of S. Yeah. So definitely it's multiplication, right? It's multiplication. So what is V naught of T? V naught of T is going to be minus RC dVn of T by dt. Multiplication of S in frequency domain is differentiation in time domain. Now, can we remove the negative sign? Can we just remove that negative sign there? Can we remove the negative sign? What should be the design? Find V naught of S by V in of S. Find V naught of S by V in of S. See, or if somebody asks you, gives you a question like this in the exam, and he says, recognize the circuit. What do you mean by recognize the circuit? Whenever somebody says recognize, it doesn't mean that you have to keep staring at that circuit, right? That's not recognition. Because there are so many ways of connecting resistors and capacitors, you keep on staring at that circuit. That's not what you have to recognize, right? Recognize means a system is always governed by its transfer function. Whenever a network is given with capacitors and resistors connected, then by looking at the transfer function, then you can recognize what sort of function the amplifier is doing, right? Okay, so let's not stare at this diagram now. We will calculate the transfer function. For that, we have to replace capacitor by 1 by SC. And we all know that the voltage at non-inverting, this is V1, is same as V2, right? Or VP is same as Vn. Voltage at positive is equal to voltage at negative. Now, what is the voltage at positive terminal by, see, I'm fed up with KCL, entering, leaving. I just apply voltage division here, right? What is voltage division? When can you apply voltage division? When the same current should flow through both the resistors. You can apply voltage, same current. There's a single voltage and same current is flowing. You can apply voltage division. So same current, you can apply voltage division. Same current here, you can apply voltage division. So what is VP? VP is going to be Vin into R by R plus 1 by SC. It is going to be Vin into SCR by 1 plus SCR. Similarly, what is Vn? Any current that comes from the output is the same current flowing, so you can also apply voltage division. If you don't remember voltage division formula, you can apply KCL, right? Your wish. So Vn is going to be V naught into 1 by SC by R plus 1 by SC. It is going to be V naught by 1 plus SCR. So according to virtual ground, Vp is equal to Vn. So your Vin SCR by 1 plus SCR is going to be V naught by 1 plus SCR. So 1 plus SCR, 1 plus SCR cancels. V naught by Vin is going to be RC of S. Oh God, this fellow has come. Now in the previous example, you can see that it is minus RC of S, all right? Minus RC. The negative sign indicates that it's an inverting, but now it is RC of S. So what name can you suggest here? The circuit is a non-inverting differentiator. Non-inverting differentiator. Right? It's a non-inverting differentiator. How do you spell differentiator? F-E differentiate. Yeah. It's a non-inverting differentiator. In the previous example, you have a minus RC of S, but in this example, you have plus RC of S. That's the only difference, right?
Dad, is that your classes? But what I'm not talking about, they listen.
Of course, they will listen. Come say hi.
Mom said no.
Come say hi. Yeah. Oh, no. Just say hi and go.
Hi.
Close the door. Very good. So you've got RC of S. Good. So the circuit is a non-inverting differentiator. Sketch V naught. Sketch V naught. Okay, so how do we solve this problem? We already know the answer. V naught is minus RC dV in of t by dt, right? So R and C values are already given. What is R multiplied by C? So I made it little simple because R is 100K, that's 10 power 5, and 10 nano, it's 10 power minus 8. So I don't want to struggle with mathematics. So this is just simply 1 millisecond, right? So we've tailored the value such that you get a standard 1 millisecond, right? That's tau. Now, minus RC dV in of t by dt. But what is V in? How do you characterize a sine wave? A sine wave moves like this with a certain time period. How do you characterize a sine wave? To characterize a sine wave, we need two things. One is how big is the waveform, right? That's the peak value. And the second one is how fast the wave moves, which is the frequency or the period, time period, right? So how do we, if I have a sine wave, and don't forget the DC here, there's a DC here and sine wave here with a certain time period T, right? So this is 1 volt and here you have 2 volt. This is a peak VM. Yeah. How do you characterize a sine wave? Can I say that V in is VDC plus the sine wave sits on that clamps, right? It's got a new DC value of 1 volt plus Vm sine omega t. Can I write like this, right? It's got a DC of 1 volt plus the sine wave is naturally Vm sine omega t. What is DC? It's 1 volt. And what is the peak? The peak value is 2 minus 1. The peak value is 2 minus 1, which is 1, into sine omega. Sine omega. Omega is 2 pi f or 2 pi by t. So it is 1 plus 2 minus 1 is 1 sine 2 pi by t. 2 pi by t. T is 10 milli. So it's 200 pi t. It's 200 pi. 1 plus sine 200 pi t is how you characterize the sine wave. So now that's it. You know V in, you know R, you know C. You just go and substitute in the output. So the output is going to be minus RC d by dt of V in of t. So it's 1 millisecond d by dt of 1 plus sine 200 pi t. 1 plus sine 200 pi t. Yeah, is it 200? Yeah, 200 pi t. Yeah, what happens when you pass a DC to a differentiator, right? So what is differentiation of a constant? When you differentiate a constant, what do you get? You get 0, right? What is differentiation of a sine function? Differentiation of sine is going to be cos 200 pi t, but the variable of interest is time, right? So you have to multiply by 200 pi. Yeah. Oh, now what is pi value? Approximately pi is 3.14 into 2, 3.14 into 2, 6.28, right? So it is 0.628, 0.628 cos 200 pi t. This is your output, right? So how do you sketch the output? When time t is 0, what is cos 0? Cos 0 is 1 into 0.628, negative numbers at time t equal to 0 minus 0.628. And thereafter, the nature is almost like the sine function, 6 to 8. And what is the period? The period still remain 10 milliseconds. So it's not changed. When you pass through a differentiator, what you change is the sign changes to the cos signal, right? It's still got 0.628 minus 0.628 cos 200 pi t. And what is the relationship between the time period and the frequency? Time period and the frequency, right? Frequency. F is always what? What's the relationship between the time period and frequency? What is time period? What is frequency, right? So time period says that it takes t seconds for one cycle, right? It takes t seconds for one cycle. But frequency is how many cycles in 1 second, right? How many cycles, right? It takes t seconds for one cycle. What's frequency? In 1 second, how many cycles? How many? So that's going to be 1 by t, right? This is going to be 1 by t. So this is your f, the frequency. The frequency will always tell you the number of cycles per second. The number of cycles per second. So that's a relationship between the frequency and the time period. Time period always tells you that it takes t seconds, the 10 milliseconds is the t seconds for one cycle, right? Now, what about an integrator? So, integration, differentiation, you have to just interchange the position of the resistors and the capacitors, right? Okay, sorry, let's do by frequency domain, right? That's much simpler. So tell me V naught of S by V naught of S is going to be minus R2 by R1, minus R2 by R1. So this, if this happens to be like an inverting amplifier, because once you convert it into an impedance, its units is ohms. Its units is, you can almost treat that like a resistor. Its units is ohms if you multiply by S1 by SC. And then it allows you to use the basic inverting amplifier formula minus R2 by R1, right? So this is minus 1 by RC of 1 by S. Oh, now there is a division of S. There is a division of S. So what do you get now? V naught of t is going to be minus 1 by RC of integration V of t dt. V of t dt, right? Or if you want to integrate, you can write 0 to t plus the, if there is any charge in the capacitor, you can have V naught of 0, something like that, right? But this is fine. Minus 1 by RC integration V of t dt. So what do you understand now? The output is proportional to the time integral of the input voltage given. That was a time derivative. Now it's a time integral of the input voltage given. Hence, the circuit is called an integrator. An integrator. Okay. Now, how can I remove that negative sign? I think now you would have got an idea. How can I remove that negative sign? To remove that negative sign, what we are going to do, we will connect a resistor, capacitor here. So this is a non-inverting integrator. So let's prove whether it's a non-inverting integrator or not. Replace capacitors by 1 by SC, right? So VP and VN both are same. So you can apply voltage division. VP is Vn into 1 by SC by R plus 1 by SC. It is Vn by 1 plus SCR. This is VP, right? What is Vn? If this is V naught and the same current is expected, right? Or if you don't like voltage division, you can apply KCL. Vn is V naught into R by R plus 1 by SC. V naught into SCR by 1 plus SCR. We know that Vp equal to Vn. This is called virtual short. Right? This you have to apply only when the gain is high. So now Vp is Vn by 1 plus SCR is V naught into SCR by 1 plus SCR. So what is V naught by Vn? Is going to be 1 by RC of 1 by S. So this is the circuit is a non-inverting integrator. The circuit is a non-inverting integrator. Oh. Okay, shall we take a break? Right, so when we come back, we will see more circuits. Yes, we Okay, so let's get started. Can you hear me? Everyone, can you hear me? Can you hear me? Okay. Recognize the circuit. Recognize the circuit. Recognize the circuit. Can you hear me? Can you hear me? Somebody say yes. Can you hear me? Okay, thank you. So recognize the circuit. I told you, recognizing circuit does not mean staring at that circuit. We have to, the system is always governed by its transfer function. You have to find the transfer function, right? Now, you can apply voltage division when the same current flows through the resistors, right? Two resistors. What if both resistors are of same value? Same value. Then how much is going to be your Vn now? This Vn is Vp. The same current here, right? Or you can apply KCL if you want. Your Vn is simply going to be V0 by 2, which is Vp, right? Or you apply KCL. Your Vp and Vn both are same. Now you can apply KCL here. Sum of currents that leave a junction is 0. Sum of currents that leave a junction is 0, right? So it is Vp minus Vn by R plus Vp by 1 by SC plus Vp minus V0 by R is 0. Am I right? But what is Vp? Vp happens to be V0 by 2. Vp happens to be Vp minus Vin. This is Vin. Vp minus Vin, right? Vin by R. Vp happens to be V0 by 2. V0 by 2 by R. Let me write it like this. Minus Vin by R plus Vp, which is V0 by 2 into SC plus Vp minus V0. Vp is V0 by 2 minus V0 by 2R. Let's see, right? Okay, now V0 by 2R and minus V0 by 2R both get cancelled here, cancel. So what do I get? I get Vin by R is going to be V naught into SC by 2. So what is V naught by Vn? It's going to be 2 by SCR. 2 by SCR. So V naught by Vn is 2 by RC of 1 by S. So this is also a integrator, but with some gain. So there's a guy called Debu. I think there's a Debu integrator, right? See, that's a good thing about analog field, right? Analog engineers don't get Nobel Prize. You're right. Just because you build a circuit, nobody is going to give you a Nobel Prize, right? You can have a current source by a name like Wilson's current source, Widlar's current source, Holland and Debu integrator, Darlington pair. Nobody is going to give you a Nobel Prize. But what you get in return in this field is a name after every circuit, right? So you build a circuit, the world will know with your name, right? So that's satisfactory, right? So 2 by RC of 1 by S, this is a non-inverting integrator with gain, with some gain, right? That's a Debu integrator. Right? Okay. Fine. Yesterday, we have seen two amplifiers. One is the non-inverting amplifier. The other one is the inverting amplifier. Both these amplifiers are voltage sources. They are not current sources. They are voltage sources. One is the voltage control voltage source. The other one is current control voltage source. Voltage control voltage. And the other one is current control voltage. But we are still have to do the other two amplifiers. So there are four types of amplifiers. Voltage amplifier, trans resistance, which we have seen, current amplifier, and trans conductance we have not seen, right? Current amplifier is current controlled current source. Transconductance is voltage controlled current source. So two current sources we have to see now. Okay. So what is a current source, right? Current sources. So we all know that current sources should have high impedance, right? High impedance. Once again, we will see voltage sources means which has low R0. Current sources means which have high R0. So let us again have a quick review again, once again. Suppose I want to build a 1 milliampere current source. A 1 milliampere current source. If the load varies from 1K to 5K. So I have a load that is varying from 1K to 5K, but the current flowing to that load should always remain constant. So you put 1K, 1 milli, 2K, 1 milli, 3K, 1 milli, 5K, 1 milli. So however you change the current, the load. So this box we have to build. This is the box that we are going to build. And the load here is varying from 1K to 5K, but the current should always remain 1 milliampere, right? So it's always 1 milliampere. So how are you going to design this box, such a box? How are we going to design such a box here, right? Such a box. This box, this is the two-terminal box. We have to design this box now, right? How are we going to design such a box? A 1 milliampere current source. Now, the first time when I've studied current sources was probably in any basic network book. You just open, they say that we can design a simple current source with a voltage source in series with resistor. So this is the first impression you get. You open any book, they say that you connect a voltage source because you want current. You want current, naturally there should be a voltage and there should be a resistor. That is when you can generate a current, right? Because we don't have current sources. If you want to build that current, there has to be a voltage source and a resistor. And here you can connect RL, 1K to 5K. Or if you want, you can have a source transformation for this, right? So what is source transformation? You can have this as V by R in parallel with R, right? A source transformation for this box is V by R in parallel with R. And here you have RL, 1K to 5K. Now tell me, current will always choose which path? Low resistance. So suppose you want this to be 1 milliampere, where this current should travel? This current should travel to the load. It should not travel to the resistor. It should not travel through the resistor. That means this current 1 milliampere, if you want it to flow, this R should be much, much greater than. If R is far greater than RL, then only all the current will travel through the load. R should be far greater than RL. That means let R is 1 mega ohm. 1 mega ohm, right? So why I'm saying 1 mega ohm is, see, suppose 1 mega ohm plus 1 kilo ohm. R is 1 mega. If 1 mega ohm plus 1 kilo ohm is what? 1 mega. 1 mega ohm plus 2 kilo ohm, 1 mega. 1 mega ohm plus 5 kilo ohm, 1 mega. So these two resistors are in series. If you see in the first diagram, the two resistors are in series. What is 1 mega ohm plus 1 kilo ohm, 1 mega ohm plus 2 kilo ohm? So the overall resistance remains unchanged, right? And the overall current will always be constant. That is the criteria. So R is 1 mega ohm. If R is 1 mega ohm and you want 1 milliampere, your V minimum should be 1 milliampere into 1 mega ohm, which is 1000 volts. Just tell me, can you physically realize this circuit, right? So we all know that if you want current, you need a voltage and a resistor. That means what? You have to build a circuit where there is 1000 volts with a 1 mega ohm resistor in series, and you can have a variable resistor 1K to 5K. Now, what will be the current here? I. If it is 1K, 1K plus 1 mega is still 1 mega. 1000 plus 1 mega is 1 milli. 1K, 1 mega plus 2K, 1 mega plus 4K, 1 mega plus 5K, the current will always remain constant, 1 milli. But just tell me, is it possible to have 1000 volts and then 1 mega ohm? So this, what is the disadvantage? The disadvantage is clearly seen. And moreover, look at the fun thing here. What is 1 milliampere into 1K? What is 1 milliampere into 1K? 1 milliampere into 1K is 1 volt. You have given 1000 volts, nothing is going to the load, 999 is dropped in the source itself, right? So is it a good circuit where everything is eaten by the input source? So what is the disadvantage? There is a large power dissipation in the source here, source resistance. So the whole voltage is dropped there, right? And the second disadvantage is, tomorrow I want to change this 1 milliampere to 2 milliampere or 5 milliampere. What will you do? If you want to change it to 2 milliampere, you have to have 2000 volts. So that's rubbish. So you cannot, there is no current range in this circuit. There is no current range. So this topic was probably a great motivation to study analog. If somebody asks you, why study analog, right? Just ask him to do this. You design a 1 milliampere current source, and I have a load which is changing from 1K to 5K, right? So it's impossible unless and until you come to the world of nonlinear devices like the BJT and MOSFET, and if you study op amps, all these fascinating devices, then you realize that this is possible, right? 90% of analog runs on current sources, I told you, right? All biasing structures are current sources. Differential amplifiers need current source for biasing. All current mirrors are current sources. So many hundreds of current mirrors are there. All are current sources. They all have high impedance, but they give 1 mega ohm. What is 1 mega ohm? 10 mega ohm, 50 mega ohm, but they don't work with 1000 volts. They just work with 2 volt, 3 volt, 5 volt. Are you getting it, right? So if you come to the world of analog, you have so many circuits which are far better current sources than this, and they don't work with 1000 volt. They just work with 1 volt. I'll show you with 1 volt how you can build, right? Current source 1. First I'm giving you one simple current source. So you want 1 milliampere current source. I told you we can program it, right? I'll connect 1 volt with 1 kilo ohm. That's enough, right? 1 volt, 1 kilo ohm. So now this is the box. I'm talking about, there's a box. So you can put this in a box and give it to your friend, and you can tell him that you have built that current source, right? Oh my God, can I pull this? Yeah. You can put this in a box and give it to your friend. Right? Just put this in a box and give it to your friend, and let your friend connect the load RL here. It'll be more fun now, right? And ask him to change that load, right? So there's a two terminals are there. This is the whole box is our current source. Now, according to virtual short, this is ground, so this is 0. And what is the current I? Current I is going to be 1 minus 0 by 1K, that is 1 milli. Now you tell me, can op amp draw current? No. This current is nothing but the load current. The load current IL is nothing but I is 1 milliampere. So it's more fun, right? So we have built a pretty nice current source of 1 milliampere where the current varies, if the load varies from 1K to 5K, the current will always remain constant, right? So now you tell me, can you build these current sources with a simple passive component, right? Voltage sources with resistors? No, right? you should have 1000 volt supply, right? You should 1000 volt. That's a big number, right? You have to run a cable from this Nagarjuna Sagar power generating station here, right? Okay. So, yeah. So all these current sources are far, far better than the current source that we have designed now, right? Current source 2. Current source 2. It's not that you have to give that 1 volt only to non-inverting and inverting. You can give it to non-inverting also, 1 volt. So then it becomes a voltage controlled current source. So now you can give this box to your friend, right? This box, and ask him to connect the load here. Ask him to connect the load here, RL, and let him change this load, right? So what's the surprise now? You keep on changing the load, 1K and 2K and 3K and 4K and 5K, but op-amp, with all the struggle of negative feedback, he will always bring 1 volt here. He will always bring 1 volt, right? The moment you change, it'll come to a point and bring 1 volt. You just change the resistor again, again 1 volt. So you keep on changing the resistor, you always find 1 volt. When you always find 1 volt, what is the current I? This current I is same as IL, right? Op-amp draws, what is the current flowing through op-amp? This is 0. So this IL is same as I. So IL equal to I equal to 1 minus 0 by 1K, that is 1 milliampere. So you always have a current of 1 milliampere flowing. So this becomes a voltage controlled current source, something like the input is in voltage form. But the previous one is the input is current, right? Okay, so whatever it is, this is also a pretty nice current source. So you keep on changing the load, your current will always remain constant. Okay. So what do we call these current sources? When if you are controlling a current source with voltage, I told you non-inverting terminal is for voltage and inverting terminal is for current. So now I'll show you that there's a difference between the first current source and the second current source. The first current source, this one, is called a current controlled current source because the input is given to inverting. The second one is a voltage controlled current source because the input is given to non-inverting. Okay, so let me draw this voltage controlled current source or transconductance amplifier. So what the transconductance amplifier will give you, it gives you I naught equal to Gm times of Vs. I naught equal to Gm times of Vs. And what does Gm stand for? Gm stands for transconductance. Gm stands for transconductance. And whenever you're designing an amplifier, your I naught should be independent of load RL. So even you change RL, current will always remain same. So the same thing I'm going to draw, right? This same structure, but in a different fashion. So this is a transconductance amplifier. Now find the relation between I naught and Vs here. Apply virtual short and tell me. Find the relationship between I naught and Vs. This is my third current source, right? Current source 3. See, in a design course, this is not a device course. I told you it's a design course. With the help of devices, we make different designs. So when you study a design course, you will understand that there is not one way of getting a problem solved, right? There are so many people working on op amps and circuits. Do you think all are using the same differentiator and the same integrator like that? No. Each one will have his own way of design. The outcome is same. They are all integrators, but one is a Debu integrator, one is a normal integrator, one is a non-inverting integrator, one is the inverting. So for any problem, for any problem to arrive at a solution, there are so many ways. That's the beauty of a design course. When you do a design course, it's like making a car, right? It's not one way of making a car. So many ways. The basics are same, but the final output, if you look at the cars, they all have different characteristics, right? And the best way to learn a design course is to see what others have done. Is it not? So you should not, initially itself, you should not start off with your own designs. Because when you see what others have done, you will learn the rules of the game. So once you're habituated with the rules of the game, then you can have your own word of expression. You can have your own designs later, right? But not first class itself. First class, you study a non-inverting amplifier and then you start designing on your own. No, right? Don't do it. Just see, just open the box, see what others have done, right? That's the best way to learn. Analyze them. Okay. So how do we solve this? The voltage at non-inverting is Vs, so the voltage at inverting is also Vs. All right? Vs. Do you want me to apply again KCL, or can I apply current division formula? I have not applied current division. Is I naught R1 R2 R3, and here the voltage is Vs. It's a current source. This is a current source, right? Current source is I naught. So we have I naught flowing here, and it is split into two currents. But can op amp draw current? No, right? Now you can apply current division if you want, or just apply KCL if you want. Entering, take one current here, the same current will flow here. I1, I2 you can take, right? I1 flows through R1, I2 flows through R2 and R3, and you can solve. There's nothing, right? But if you remember current division formula, I told you that the branch current, suppose this current is Ix, what is the relationship between Ix and I naught? What is the relationship between Ix and I naught, right? Ix equal to I naught into opposite arm resistance, R1 by R1 plus R2 plus R3. And what is Vs? It is Ix into, what is Vs? It is Ix into R3. R3, which is I naught into R1 by R1 plus R2 plus R3 into R3. Am I right? So what is I naught? Defining once again transconductance. Transconductance, GM, it is output current by input voltage, R1 plus R2 plus R3 by R1 R3 is your GM, right? So, or I naught is R1 plus R2 plus R3 by R1 R3 times of Vs. So this is of what form? This is of the form I naught equal to GM times of Vs. All right, I naught equal to. So definitely this is a transconductance amplifier, and you can always validate your answer by the units, right? What is R1 plus R2 plus R3 units? What is ohms plus ohms plus ohms? R1 plus R2 plus R3, ohms plus ohms plus ohms. It is ohms, right? In the denominator, you have ohms into ohms. What is ohms into ohms? It's ohms square. The numerator has ohms and the denominator has ohms into ohms square. Ohms by ohm square. Ohms by ohm square is 1 by ohm. That's conductance, mho, right? Or Siemens. So please, you can as well take some I1 here and I2 here also, right? I1 and I2, and then solve it. It doesn't matter. Or you want to apply current division, you can apply. Current division is applied when a bunch of resistors experience the same potential difference and the current is dividing, right? So if you can sum up R2 and R3, that's one single resistor between this node and ground, and you have R1 also, right? Something like parallel connection. You can apply current division. You don't like current division, just take I1 here through R1 and I2 through R2, and then solve by Kirchhoff's law. I0 equal to I1 plus I2, and you can take a node and do it. It's your wish. Okay. So non-inverting amplifier is a voltage amplifier, trans resistance. This is trans conductance. What is the last dependent source we are left with? The last dependent source is current control current source. It's called current control current source or current amplifier. Current amplifier. Your I0 should be K times of IS. Current amplifier, right? So input is in current form. The output is also in current form. So this is a current amplifier or a current control current source. Okay, so how do we solve this? You can take an extra node here, Vx, or you can apply current division. Let me do by KCL. So the current entering is equal to the current leaving. All right. So what is I0? I0 equal to Vx by R1. This is leaving current. I0 equal to Vx by R1 plus Vx minus this node is at 0. This node is at 0. So it's Vx minus 0 by Rf. By Rf. So I0 is Vx into 1 by R1 plus 1 by Rf. 1 by R1 plus 1 by Rf. This is KCL at this node. But what is the current flowing through RF? If op amp draws no current, 0 ampere, If this is IS, this current should also be IS. Am I right? So what is Vx, by the way? This is RF. Is virtually 0. Here you have IS. This is Vx. This node. So tell me, what is IS in the feedback resistor RF? IS equal to 0 minus Vx by RF. Or Vx is minus IS into RF. Substitute 2 in 1. Substitute 2 in 1. So you get I naught equal to minus IS into RF into 1 by R1 plus 1 by RF. Now this looks like the same, the first amplifier, non-inverting amplifier gain. What is the non-inverting amplifier gain? I naught equal to minus of 1 plus RF by R1. Here we are just getting the negative sign, but otherwise this is the formula we have got for voltage. Do you remember? What is the gain? V naught is 1 plus R2 by R1 or 1 plus RF by R1 times of IS. The same gain we are going to get here, right? I naught is except for the fact that there is negative sign, right? So two equations, you substitute 1 and 2, you get the answer, right? I naught is K times of IS. I naught finally is K times. What is the value of K? It is minus of 1 plus RF by R1, right? Or if you don't like this, you can apply current division. I told you. Here there is I naught. And here you have R1. And here you have RF. Yeah, the other end of RF is at 0 volts. 0 volts. And, yeah, be careful with the current direction. What is IS here? IS is going to the node. IS is going to the node. IS. This is Vx, right? Yeah, now you tell me, if I naught has to split in two resistors, are the two resistors experiencing same potential difference? Are the two resistors experiencing same potential difference? Yes. Vx minus 0 and Vx minus 0 through RF. Both are experiencing. So now you can apply current division also. Through current division rule, if this is IS, what is the current in the opposite direction? Minus IS. Minus IS is the current equal to total current into opposite arm by sum. So I naught is going to be minus of 1 plus RF by R1 times the IS. So this is, if you remember current division formula, otherwise what is there? Just blindly apply KCL, entering equal to leaving, entering equal to leaving, entering equal to leaving, you get. So the I naught is minus of 1 plus RF by R1, the same thing we got by current division, am I right? హలో అలా ఇది పేజెస్ ఎట్లా ఇంక్రీజ్ చేయాలి? 92 వరకు ఉంది. ఎక్కడుంది? అవునవును ఉంది. డిలీట్ ఫ్రేమ్ అని ఉంది, డూప్లికేట్ కీ.
సార్ డిలీట్ ఫ్రేమ్ కొట్టకండి. ఇక్కడ 117 ఉంది కదా.
నానా ఇది 92 వరకు ఉంది పేజ్ ఇంక్రీజ్ చేయాలి.
పక్కన రావట్లేదా స్లైడ్?
రావట్లేదు. యాడ్ ఫ్రేమ్ అని ఎక్కడ వస్తుంది?
మీకు వచ్చింది కదా.
వస్తుంది నాన్న, థ్యాంక్ యూ. చెప్పు వెంకట్, ఎట్లా వస్తుంది?
ఫైన్. ఇది కొద్దిగా ఈ కలర్ ఎడిటర్ ఉంది కదా, అది మీరు సైడ్ లో చేసేసుకొని కొద్దిగా స్క్రీన్ ఎన్లార్జ్ చేయండి.
ఇక్కడ కింద యాడ్
వచ్చి ఈ కలర్ ఎడిటర్ కొద్దిగా సైడ్ కనేసేయండి. కొద్దిగా స్క్రీన్ ని మొత్తం ఎన్లార్జ్ చేయండి సార్.
ఇది రావాలి. సర్లే
సార్,
ఇది పోయింది.
ఈ కలర్ ఎడిటర్ ని కొద్దిగా అవతల కనేయండి సార్.
ఎటు?
స్క్రీన్ లో కనపడకుండా చేయండి. మీకు కనిపిస్తే చాలు, మాకు కనిపించని అవసరం లేదా. కొద్దిగా అవతలి కనేయండి.
ఇటు సైడా?
కింది కనేసేయండి మొత్తం. మీకు కనిపిస్తే చాలు అంతే.
ఇప్పుడు నేను దానికి ప్రెస్ చేసుకోవాలిగా.
మీకు కనిపిస్తుంది కదా.
ఇప్పుడు ఓకేనా?
కొద్దిగా స్క్రీన్ ని ఎన్లార్జ్ చేయండి సార్.
ఎన్లార్జా?
మీకు ఒక పిక్ పంపించాను చూసారా, మీ వీడియో ప్లే అవుతున్న దాని పక్కన కొద్ది గ్యాప్ ఉంది కదా, వైట్ బ్లూ రెండు మిక్స్ అవుతుంది. స్టూడెంట్ కొద్దిగా ఇబ్బంది ఫీల్ అవుతాడు.
ఓకే, ఇప్పుడు ఓకేనా?
ఇప్పుడు కొంచెం స్క్రీన్ వైట్ స్క్రీన్, మీ లోగో ఉంది కదా, ఏస్ లోగో, కొద్దిగా రైట్ సైడ్ లో పెట్టండి. కొంచెం కొద్దిగా అక్కడ గ్యాప్ వస్తుంది. కొద్ది గ్యాప్ వస్తుంది నాకు.
ఇప్పుడు నేను కలర్స్ చూస్ చేసుకోవాలంటే నాకు కష్టం అవుతుంది. నాకు రెండే కలర్ కావాలి. బ్లూ కనబడట్లేదు నాకు, బ్లూ కలర్.
కలర్స్ ఇక్కడ లెఫ్ట్ సైడ్ డౌన్ లో ఉన్నాయి కదా.
లెఫ్ట్ సైడ్ డౌన్ లో ఉన్నాయా?
సరే, కానివ్వండి.
ఓకేనా? So this is I0. You have two resistors, R1 and RF. That's gone somewhere. RF. Here this is IS. So this current is minus IS. Minus IS equal to I0 into RF by R1 plus RF. So I0 by IS is minus of 1 plus RF by R1. Okay. Fine. So this is what amplifier is this? This is the current amplifier. Am I right? Yeah. Now, what is the problem in these two current sources? If you see, one is a voltage controlled current source and the other one is a current controlled current source. So these two circuits are very popular. Okay. But the problem here is they all have floating load. The load does not have a ground node, right? It's not connected. It's somewhere hanging in the middle. So this is called the floating load. It's called the floating load. But if I want a current source with grounded load, right? So always the load should be connected somewhere to the ground. You cannot connect somewhere in between, right? So to have a grounded load problem, this is an IES problem. You have to find the current. Find I0. First, let us do this problem. Give the volts here. R, RL, this you can have whatever, RX. Okay. Yeah. Find I0. Solve this problem. This is an IES problem for 10 marks, a simple problem, but this is one of my favorite circuits, right? One of my favorites. I'll tell you why it is. After calculating, first it's given for 10 marks, just 2-3 steps, you can finish it. Let's get the marks first, and then we will think, what this circuit is actually trying to tell. Every circuit has a language to speak, right? So what language is it speaking? You have to see it. Okay. So let's solve it. We don't know what is this. I'll just call it V naught. This node also we don't know. We'll call it Vx. All right. So let us solve this problem. Oh, there's a blue one. It's a black. Okay. So how do we solve this? If this node is Vx, then this node is also Vx. Can op-amp draw current? No. So what is the relationship between V naught and Vx? This current is 0. V naught minus Vx by Rx equal to Vx by Rx. So your V naught is going to be 2 times the Vx. Your V naught is going to be 2 times the Vx. Now, let us apply KCL here. Entering current equal to leaving current. Leaving current. This leaving, but this splits into 2, right? So what is entering current? KCL. It is V minus Vx by R is equal to I naught plus Vx minus V naught by R. Vx minus. Just observe this equation. So this is the equation which I like, right? And somehow it has become one of my favorite circuits in analog, right? So what is V minus Vx by R? It is V by R minus Vx by R is equal to I naught plus Vx minus V naught. V naught is 2Vx, so it's minus Vx by R. Can you see that the Vx by R and the Vx by R here gets cancelled, and your I naught is simply V by R, right? So this is given for 10 marks in IES exam. Of course, by you apply KCL, you get the answer, right? But fine, the examiner didn't ask, right? He didn't ask, unfortunately, he didn't ask, what is this? What is the purpose of this circuit? What is this circuit meant for, right? Nothing. He just said calculate I naught 10 marks, right? Okay, we calculated it. Any guess what this circuit does, right? Any guess what circuit does? Any guess what this circuit does, right? I is V by R, right? Now, just remove the op-amp portion and just see the first portion, VR and RL, VR and RL. Is this how I started current sources? Is this the problem I had in mind when I opened a network book? I found a voltage source and a resistor and RL. So my head goes banging here, right? When I first see, I open a networks book and I want to design a current source, right? So this is something, this is the first impression you get. You have a V, you have an R, and you want V by R. And you want all that V by R to flow through RL. You want all that V by R to flow through RL, but it's not possible. They say that you need 1,000 volts, right? You need 1,000 volts. And then the same first circuit is here, lying here. The first circuit is lying here. VR. This is where I started. I said I need 1,000 volts. And then something comes here, some box comes here, and it fulfills my idea, right? So what is that extra thing that comes? Do you remember I've drawn a Norton equivalent here? What's the Norton equivalent for this? The Norton equivalent is actually V by R in parallel with R, and you have an RL here, RL. And the whole current I is now equal to V by R, surprisingly. Now, how is this possible that the whole current I is V by R? Because current will always choose which path? Low resistance. What happened to R? The whole V by R is traveling through RL. Nothing is flowing through R. Then you get an idea, who is this box? Is this box giving you minus R or something, right? Is this giving you minus R or something? Because what is R parallel with minus R? R parallel with minus R is R into minus R by R minus R. It is something divided by 0, it's infinite. Boom, just those two resistors just go, they just vanish in the circuit, and the whole current is sinking through RL. And now if you say, from where did I get that minus R? I told you, how will you simulate minus R? You can simulate minus R, V by R, this is R here, and this is RL. You can simulate minus R if you have an amplifier of gain 2 and you stuck a resistor between the input and output. And this guy becomes minus R, comes in parallel with R, and R parallel with R, minus R, it becomes infinite. And the whole, these two sections just vanish from the circuit, and the whole current I becomes equal to V by R, just keeps flowing like this. And now if you say that, how do I design that minus R? I need an amplifier of gain 2, right? Okay, I just remove the Norton equivalent and come back to the Thevenin equivalent here. This is V and R, source transformation. Here, this is RL. Now you tell me, I need a non-inverting amplifier of gain 2, So I put two resistors, RX, 1K like this. And then between input and output, I put R. That became my IES problem, right? So this is an IES problem. The IES examiner just said, what is I naught? Just calculate, take the marks, right? But there's something to do. You are simulating a negative resistance here. So a negative resistance. How is this possible? See, still, you can apply KCL here and tell me, what is happening if I apply KCL? Entering current is equal to leaving currents, right? So it's interesting when you apply KCL. What is entering current here? V by R equal to, this is IX, this is I naught, and this has to be minus IX. This is IX plus I naught and minus IX. What is happening now? This minus IX and IX gets cancelled. What do you mean by negative current? It's a current that's actually flowing in the opposite. It's exactly the IX that's flowing in the opposite. That means what? It's this current that is going here. There's a current that is coming in this direction. Because the output is high, this is low. The op-amp is supplying that current in the opposite. Please, negative resistance means amplifier. That's a statement. If somebody says that I have negative resistance, don't believe him, just tell him you have an amplifier. Because if you have an amplifier, it has a gain. And if there's a gain, and gain means what? 2 times. This side is 2 times more, this side is less. The current is actually flowing in the opposite. This is Vx, this is 2Vx, right? 2Vx. Who is at higher potential? Who is at lower potential? V naught is higher 2 times, Vx is, so the actual current is flowing in the opposite direction. To nullify this current, the net effect is that the whole V by R sinks through RL, just boom, keeps on flowing through RL. So there's so many components now, keeps flowing, and this R and minus R, this set cancels each other. This is called the Holland current source. So we are applying, so it's not that in the introduction, just introduce negative resistance and leave, right? Our main aim is that we are going to use whatever you have studied in the introduction program, we are going to apply them again and again. That's how the course is designed, right? I've designed the course in such a fashion that I'll give you some introduction, and based on that introduction, we will stay there till the last class. We keep applying them again and again in our future designs, right? So negative resistance means the current is flowing in opposite. That means what? There's a gain. The output is higher potential, the input is lower, there's a gain. So there's always a current flowing in the opposite direction. Now you tell me, why in an inverting amplifier there's a negative sign? Why in an inverting amplifier there's a negative sign? There's a negative sign in inverting amplifier, minus R2 by R1. That minus, you all know, it indicates phase shift, but that minus sign indicates that there's a source of power. The actual current is always flowing in the opposite. It's not this current that is going in the feedbacks here. So when I draw an inverting amplifier, and you have a gain at the output, the actual current is always flowing in the opposite direction, right? So that means who is from the power supply is the amplifier. The op-amp has a source of power, and the actual current is always flowing in what direction? The opposite direction. Don't forget that. Whenever a negative sign comes, indicate that there's a source of power. There's an active device. Negative resistance are simulated using active devices. Passive cannot. Are you getting? Yeah, in EDC, when you study the tunneling effect and the tunnel diode, somewhere you find, but not so well as an op-amp. Op-amp, you name minus R, minus 2R, minus 3R, we can tailor any value of negative resistance. Are you getting? By this simple circuit. Just change the gain, you have a different value of negative resistance. The gain is 2, so it's minus R. The gain is 3, it's minus 2R. Gain is 5, minus 4R, something like that, right? Okay, but this is an IES problem. You can solve till here, and you can simply mention a statement saying that this current source is called what current source? Holland current source. And the op-amp simulates a negative resistance. An op-amp simulates what? A negative resistance. So this is, what name shall we give this? Holland current source is the name. Holland current source. With grounded load, right? With grounded load. Holland current source with grounded load. Okay. Find I naught. Find I naught. find I naught. Find I naught. Right. Yesterday, you've been telling me that there's a game called what? The Pac-Man, right? Now, the Pac-Man keeps moving, so around wherever he finds a chance. So let's apply KVL like the Pac-Man game. This I naught here. What is this voltage here? VD is 0. VD is 0. And VD is 0 because V1 and V2 both are same. So you can take VD 0 when you are applying KVL, right? So this is I naught. What if I take some current I here? Any current that comes from the positive, the same current is expected in the negative. Can op-amp draw current? No. Same current I. This is I, this is I. See, there's only one unknown I, right? There's only one unknown. But if you take nodes V1, V2, V3, V4, it becomes cumbersome. So now, instead of KCL, we are going to apply what? KVL. Now, how does a student knows that he has to apply KVL and KCL? Simple. I'll give you a simple example. See here. Suppose you have resistors like this, right? Resistors like this. And there's a voltage, V. There's 1 ohm, 5 volt. There's 1 ohm and 2 ohm and 3 ohm and 4 ohm, 5 ohm. Now, how will you solve this problem, right? So when an amplifier looks stretched like this, stretched, there's all the resistors coming in series, something like the same current is flowing. So when it looks stretched like this, I'll be a fool if I take V1 here, and then V2 here, V3, and V4, and V5. So we don't do by the node method, entering, leaving. Instead, we say that there's only one current I flowing here, and I is equal to phi divided by all these resistors, 1 plus 2 plus 3 plus 4 plus 5. So the first impression for a student is when a network looks stretched, KVL. When a network looks something like this, right? There's a parallel connection like this, and you have a voltage source, then you apply KCL now, right? There's only single equation, KCL. So when a network looks like this, KCL, stretched KVL, right? That's logic. So by looking at this stretched network, we find that there's a single current flowing. Now, how does the Pac-Man move, right? I start here and I have to come back here. So tell me, how do I move from here? So I'll start like this. La 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 la. La 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 like that, right? This is my direction. So you can just move around, you just one equation, and then you have to cover V in, so you can take one equation here. That's enough. So a single equation will do, right? Yeah. So just tell me, what is a drop through this resistor? It's I naught into R. And then here VD, that's 0, plus is a current I here, right? It is IR plus, this is 0, plus IR equal to 0. That's it, right? So I naught into R is going to be minus 2IR. Or what is I naught? I naught is minus 2I, right? Waiting one. Okay, so give me this simple chota loop here in this, the first one. Minus to plus, one more KVL. Minus Vin plus IR plus 0 or minus 0 plus IR equal to 0. So I is equal to, or 2IR is Vin, I is Vin by 2R. So your I is Vin by 2R, but I naught is minus 2I. So what is the answer now? The answer is I naught is minus 2I and I is Vin by 2R. 2 gets cancelled. So here I naught is minus Vin by R. So remember, when a network looks kind of stretched, remember the Pac-Man game and don't hesitate to go up above the head of an op-amp, right? Just above the head and down. Just take that travel, right? Don't hesitate. Don't be reluctant. Don't stare at that network. So because KVL says that the algebraic sum of voltages in a closed loop is 0. Remember the Pac-Man game, right? Just go around and cover it, cover the loop, right? All through the resistors. So this is also a current source with a voltage controlled current source with what load? Grounded load. So when do you say that a current source is a current source? When the final I naught should be independent of RL. There should not be RL in any of the op-amp problems. No RL, right? No RL. The final result, no RL. I naught is Vin by minus Vin by R. So look at the expression, right? Very simple. I is V by R. Okay. Now, in the frequency response, I told you 4 types of filters. What are they? Low pass, high pass, band pass, and band stop. Intuitively, how you can find the type of filter? You check at low frequency and high frequency, and then intuitively draw the plot. That is one thing. Or you can as well find the transfer function. If the transfer function is of the form k by 1 plus s tau, then it is a low pass filter. Ks by 1 plus s tau, it is high pass, isn't it? This is a gate problem for 2 marks. Recognize the type of filter. A simple gate problem. Recognize the type of filter. Recognize the type of filter. Recognize the type of filter. So, what is the simple procedure that I told you? You can check the filter in the at the low and high frequency, is it not? For low frequency, omega 0, capacitor will behave as open circuit. Capacitor will behave as open circuit. Open circuit. And you get a non-zero output. This is R2, this is R1. Your V0 by Vin is going to be minus R2 by R1. Is going to be what? Minus R2 by R1. So you have some output, right? Or what is V0 by Vin? The gain magnitude. It is R2 by R1. Then what happens at omega infinite? Capacitor will behave as short circuit. Capacitor will behave as short circuit. Short circuit. Then what is V0? This is ground, so this is 0. So just tell me if this is 0, what is this node? This is 0. What is this node? 0, 0, 0. Your output is also 0. Right? Then how do you plot this? For low frequency, V0 by Vin magnitude, tell me what happens at low frequency, omega 0. Your gain is R2 by R1. The gain is R2 by R1. But at high frequency, omega infinite, it is 0. So these are the 2 points. So what does your intuition say, right? So you have a non-zero output at low frequency, and at omega infinite, you don't have any output. So what sort of filter is this? Think about it. So if I join these 2 points, I realize that this is what filter? Low pass. And the cutoff frequency, omega 3 dB, is 1 by RC. And what is the resistor which the capacitor is seeing? The capacitor has to see some resistor, right? Between its 2 plates. the two plates. So this is the capacitor. So you have a capacitor here, right? So just imagine I have a capacitor, right? This is a capacitor, right? And I'm placing two eyes of the capacitor. This eye here, capacitor eye, I'll put it here, right? This eye, I just put it here. So this guy is seeing. So when he's seeing, who does he see, right? He sees some resistor R2 here, right? C2. So tau is going to be 1 by R2 C2 by logic, by intuition, right? So this is a low pass filter, 2 marks for recognizing the type of filter. So what is the other way of doing it is, you can find the transfer function. So you can call this as Z, impedance Z. So what is V0 by V? V0 by V is going to be minus Z by R1. And Z is R2 parallel with 1 by SC2 by R1. Because those two resistors are in parallel. So now, what is R2? This is R2 into 1 by SC2 by R2 plus 1 by SC2 into R1. It is minus R2 by R1 by 1 plus SC2 R2. Now, this is of the form K by 1 plus S tau. I have given you in my introduction, right? So I've given you the type of filters, K by 1 plus S tau. It has to be what filter? Low pass. And what is the omega 3 dB? It is 1 by tau. It is going to be 1 by R2C2. All right. It's going to be 1 by R2C2. This is tau is S. Anything associated with S is tau here. So tau is R2 and C2. 1 by R2C2 is this, right? Or you can, from the transfer function, you can also put S equal to 0 or omega equal to 0. You can calculate this. So you can get the same plot, what you got. So in linear applications, what are we covering? I've given you a table. Adder, subtractor, differentiator, integrator, and simple filters, right? So these are the topics we are going to cover in linear applications. Just recognize the type of filter. This is a low pass filter. And the next year, the gate examiner said that, what about this filter? You just change the position of the capacitor here. There's also a gate problem, simple gate problem. He says, what is the type of filter? What is the type of filter? Tell me, for omega 0, capacitor will act like open circuit. Open circuit. And your output is 0. for omega infinite, capacitor will act like short circuit. Short circuit. And you get a non-zero output. V naught by Vin is going to be minus R2 by R1, or V naught by Vn is R2 by R1 magnitude, right? So now you can plot it. For omega 0, what is the output or what is the gain, right? There's no output, there's no gain. Your output is 0. At omega infinite, you get maximum output here, which is R2 by R1. So what does your intuition say? You have a high output, you have a low output here, right? Just think for a while that what happens here. You have low and you have high. So I can join these two. And I can say that this is what filter? A high pass filter, right? And what is the 3 dB cutoff frequency? It's 1 by tau. What is tau? R into C. But what is the C? The capacitor is C, right? Capacitor has two plates. Where are the two eyes of the capacitor? One in this plate and the other plate. Here there's virtual short. If you short this, the capacitor is seeing only R1, 1 by C1 R1. 1 by C1 R1, right? So, or what is the other way of doing it? The other way of doing it is your V naught by Vin is going to be minus R2 by Z. What is the impedance Z here? It is R1 plus 1 by SC. Why am I putting plus here? Plus because these two are in series, right? These two are in series. It is minus SC1R2 by 1 plus SC1R1. This is of the form Ks by 1 plus S tau. This is high pass filter, right? High pass. So this is also a gate problem for 2 marks. Very simple. Just you have to do is check at low frequency and high frequency, and then intuitively say that by looking at this, you can get 2 marks, right? Some students do by inspecting. They say that for low frequency, capacitor is open, no output. Capacitor is short, some output. No output, some output. It's high pass. First problem, some output, no output. It's low pass, right? The first problem, it is low pass. So these are 2 simple gate problems. Okay, so can we have a question answer session? Now, I want Venkat, I want you to unmute my students, right?
Hello.
Yeah.
Good evening, sir.
Good evening.
So in the previous question where we used two op-amp, can you just go to the previous pages? After the whole end. 91F, I think.
91F. This one? Oh, there's nothing here.
92 then. Where we took the loop, yeah. How are we taking the loop over the op-amps in this one?
Yeah, a loop. First of all, we should know what is a loop. A loop means you start at one point here and then you end at the same point. Are you getting? That's a loop.
Yes, sir.
Now you can bravely go wherever you want. Right? Where is it? 92?
Yes.
90, yeah. So just see the pen here. I will change the color of the pen once again. Make it, what is the brown? Yeah. So let me draw a parallel line here. So I'm starting from 0 here. Can you see?
Yes,
the
sir.
pen here?
Yes,
So
sir.
I have to come back here. First, there is a drop here of 0. First. And then there's a short from here to here, no voltage. And then there's a drop IR here.
Hmm.
Can you see?
Yes, sir.
And then there's a drop 0. And then there's a IR. And then that's it. So you
Okay.
come to here, the same point. Are you getting?
Yes, sir. Yes, sir.
Repeat.
I got it. So in 90,
G.
yes.
Can you see? Can you see?
Yes, sir. I can see. I got it.
Yeah, good. Yeah,
So 90F, page number.
90F. This one. Yeah.
So I missed the point. Why is this circuit so special?
See, the circuit so special is because whatever the current that is sinking here in R, the same amount of current is supplied by the amplifier. Now, see what is the current that is flowing through R is some value Ix, right?
Hmm.
Some value Ix that is flowing through R. In fact, that the current that is flowing through R, whatever magnitude of that current is there, it's the same thing that is being supplied here, right? So we will see here. This is actual circuit. Are you getting? So this is actual circuit. By looking
Yes,
at
sir.
this circuit, what I meant was there is a current flowing through R. There's a current I0. How V by R is I0. All that V by R is flowing through I0. So by looking at this circuit, you cannot understand. V by R, how is I0? V by R, how is I0? Then I tried to draw the Norton equivalent for this. Then I realized that there is something that is cancelling this current that is flowing through R. Who is that fellow? Is the op amp. So whatever the gain, see, okay, I don't know how to tell you. See here, I'm having V by R. Can I get the same V by R by 2V minus V by R?
Yes, sir.
Yeah. So who is 2V is the output of an op amp. V is that input, Vx. 2V minus V. See, can you see that this Vx by R is being exactly the same current is being supplied by op amp. So op amp is providing negative resistance here. So where is that 90? Can you tell me where?
90, yes.
Yeah. So this, what fascinates me here is the impedance also. R and minus R, are they cancelling each other? The net effect in the R and minus R parallel with minus R is infinite. So when it is infinite, this whole circuit is behaving like this. See here, is behaving like this. V by R and RL. This is something which I wanted because I put a box here. Do you remember? First, I put a box.
Sir.
I said, I want this. Now people will say, how can you get this? You can't get this. I just said, I want this. Then what they have done is they've put an R first here and then a minus R here. Can you see?
Yes, sir.
Then this R and minus R are getting what?
Cancel.
Are you getting? Now, the moment I put R here, I can practically build this circuit. How can I practically build this circuit?
Okay, first that was physically unrealizable, but then
yes. How you got the point now. It was totally physically unrealizable. It was just on paper. If the current source and an RL was just on paper. Then we put an R and then a minus R. Then this Norton now became a Thevenin. This is realizable by me now, V by R. And now if you ask me from where will you get this minus R? Then I'll say that I'll put an amplifier. Yeah, and then this. Then boom, I finally get this. And so if somebody says that, can you build this? Just go and show him the circuit.
Yes, sir.
Just show him. It just blows his mind. He says, oh, this is this. How you did it? First you put R here and then minus R there and say that they cancel. And then this R and this current source you physically realize with a voltage source and a resistor. And then the minus R you go and physically realize with what? A gain 2 with a resistor. Are you getting?
Yes, sir. Yes, sir. So in page 68F.
In?
68F, page number.
68F. Yeah.
Yes, sir. So you said that Miller's theorem can be applied when virtually short is there, right?
No, if virtually short is there, there's already a 0 here. That is Miller. So see, when I'm saying voltage at non-inverting is equal to voltage at inverting, I'm putting a 0 ohms resistance here. There's already Miller. There's no need for you to again do it. This
Okay,
is
it's already virtually short.
yeah, the virtually short means it's Miller actually. Voltage at non-inverting
Okay.
is voltage at inverting is that this Miller for infinite gain.
Okay.
So you don't have to again do it. But if the gain is A, your Miller, your 0 volts failed there, then you have to replace it by R by 1 plus A.
Okay.
Are you getting?
So how much large is A? It means
A is 10
A.
lakhs, 120 dB. For a 741 op amp, it's 10 lakhs. But these days you have much more, 20 lakhs, 50 lakhs, 100 lakhs. But the good thing about op amp is once you cross 1000 gain, answers are same.
Yes, sir.
Suppose my op amp is having 1000 gain. You have
Okay,
an
so
op amp
we-
of 10,000 gain, 50,000 gain, 80,000. Your output is again 1 plus R2 by R1.
So
Because
A should be around 1000, right?
it should be 40 dB more than your requirement. 100
Okay.
times more than your requirement. If
And
your
sir,
requirement is
last-
10, suppose your requirement is 10,
Yes, sir.
at least 1000.
So
That's
then
what-
we go for 1000. Yeah.
yeah. But no op amp has 1000. You can be free because every op amp gain is in lakhs.
Okay. And sir, in page number 25F.
25. 25. Yeah, 25. Yeah.
Yes, sir. How are we saying that it is open circuit and that one is short circuit? Through the op amp figure, I didn't get it.
See, by looking at a circuit, we don't know if it is open or short.
Yes,
I
sir.
can only tell you that current 0 means open, voltage 0 means short.
Okay.
Are you getting? Whenever there's a current 0, you have to imagine the model of an open circuit. Whenever there's a voltage
Okay.
0, see, you have a capacitor and the capacitor is not charging, its voltage is 0. You can model it with a short circuit. If the current flowing through the capacitor, see, suppose your battery is there, your cell phone battery is fully charged. What circuit is that?
Yes, sir.
Your cell phone battery is fully charged. It is not taking any more current. What do you say?
So short,
It's an open
short
circuit,
circuit.
right? No, it's fully charged. There's no current.
Okay,
Current
open
is
circuit.
zero. Your cell phone has no charge in it. Voltage is 0. Then it is a short. The moment you switch on, it'll start building up that voltage
Okay.
from 0,
Okay.
1,
So
2.
we are saying that it is open circuit and short circuit by the amount of current it's
Yes,
drawing
yes,
or
yes.
not.
The current
Okay.
is 0, so it's an open circuit. Voltage 0, it's a short. Something like that.
Okay. Okay, got it, sir. Thank you so
Now,
much, sir.
please
Thank you.
remove that notion from your mind that short means maximum current, open means maximum voltage. Don't do that.
Okay.
Open means current 0, short means voltage 0. Are you getting?
Yes, sir. Got it.
Yeah.
Thank you. Thank you so much.
Yep.
Hi, sir.
Yeah.
So in last question,
Yeah.
I need to get how omega 3dB equals to 1 upon tau.
Yes.
Can you please explain?
This one?
In last question, 96.
Yeah, by looking at the circuit, it is. Acha, without looking at, without the transfer function, you want me to explain?
Yes, sir.
No transfer function, nothing. By looking at the circuit here, your capacitor is there. Yeah, capacitor. Yeah, there's a capacitor. Here the op amp is virtually a short. Here there's a short. Here there is a resistor R. And here there's a voltage source. And the voltage, whenever you're finding the what you call equivalent capacitance or equivalent resistance, all voltage sources should be short. Now you remove that port. When you remove that port, you're seeing through the port. Here there is a resistor R1. So what is the equivalent resistance here? R equivalent equal to R1. You're seeing through here, the two terminals is only R1, right? So what is tau? R equivalent into C1, which is R1 C1. Are you getting? So you
Yes,
have to
sir.
see between the two terminals. There's a short, virtual short here. Is this R1 in this loop?
Yes, sir.
Yeah.
So then how omega 3dB equals to 1 upon tau?
Always omega 3 dB is 1 upon tau. Always
Okay.
omega 3 dB is 1 upon tau. Always, because that is a point where the gain will fall down by 1 by root 2. V0 by Vn. You can do like this also. There is this transfer. Yeah, now you want the transfer function. So first you explained me with the circuit. Now you want the transfer function. So what you can do is you can replace S with j omega. Are you getting? You can replace S with j omega C1 R2 by 1 plus j omega R1 into C1. Are you getting? Now, you can take this factor common and see that the cutoff frequency, or you can directly say it is Ks by what? 1 plus S tau. The tau says that the tau value is what? R1 into C1. Are you getting? Now, what is the maximum value of this? Just tell me what will be the maximum value of this. Divide numerator and denominator by S, you tell me. Divide numerator and denominator by S and tell me. Put S equal to 0. Put S equal to 0, S equal to infinite. What is the maximum value that you can expect from this?
1.
No. Maximum is at S equal to infinite, right? So divide numerator and denominator by S and tell me. What is the gain? That I already told you. R2 by R1, no. It is C1 R2 by 1 by S plus C1 R1. Put S equal to infinite here. You're going to get R2 by R1, which we have got here. Now, how do we know it's 3 dB? It is this value at this frequency. It is R2 by R1 by root 2 at this frequency. What is that frequency, omega? It is 1 by R1 C1. So you substitute omega equal to this, you will get that factor R2 by R1. Just do it.
Okay, sir.
Okay? Yeah. Next question.
Sir,
Yes.
Hello.
sir, 92.
Hello, sir.
Yeah, tell me.
Sir, 92.
92 page. Yeah.
So here I'm just confused with the current the current how you have mentioned I in the middle R.
Okay. First, I took I here. First.
Yes,
Can you
sir.
see my pen?
Yes, sir. Yes.
Yeah, this current is coming from the positive terminal. Then I said,
Yes.
whatever comes from the positive, that has to arrive at the negative, I. Then this I is same as this I, no?
Yes, sir.
Why it is
Op-amp
same?
zero.
Because op-amp draws
Op-amp 0.
no current. But
Yes.
this op-amp also draws no current. So if this is I, this is I. Here, one more I.
Okay.
This is I.
oh.
This is I. Are you getting?
Yes, sir. Yes, sir. I was just confused.
Yeah. Because op-amp draws no current. I
Yes,
took
sir.
only one current now, finally.
Okay.
I, everywhere. And then here you have I naught. Do you see? Here we have I naught.
Yes, sir.
And this
Yes,
current
sir.
should also be I naught because op-amp draws no current.
0 current.
So finally, though it is a big circuit, how many currents are there?
2 current.
Two
currents.
simple currents, I and I naught. So two equations I applied and I finished. See, you can try by KCL also, but if you do by KCL, I'm telling you, you will leave electronics. Right?
Yes, I was actually trying with KCL. I got 2 voltages and it became quite complex also.
Yes.
I was.
Yeah.
So and the 90, page number 90.
Okay. 90. Yeah. Oh,
So
again, the
I
negative
was-
resistance.
No, sir, not. I understood till there, but I was confused from the conversion of Norton to Thevenin circuit. How
That's so
amplifier of gain 2 is converted into the below circuit. That's what I was confused.
Sure, this one. Oh, well, tell me the page number 92.
90.
Yeah, tell me.
So the circuit of having amplifier gain of 2 to the below Holland circuit.
Yeah, this one.
How the op-amp got changed.
This, very good. This one I will explain here. Okay. Yeah. Here. This is an op-amp, non-inverting. And this is the first circuit we have seen in the class. This is R2 and this is R1. This is V8. This is V0. Oh, probably I would have drawn like this. That's the only difference. This is Vin. This is R1 and this is R2. Right? This is V0. So this is the same circuit. So what is the output now? The output is 1 plus R2 by R1 times a V. This is a non-inverting amplifier. No, so if both R2 and R1 are 1K and 1K, then your V2 is going to be 2 Vin.
Yes, sir.
Now, this is Vin, this is 2 Vin. The whole amplifier is having a gain 2. And now we have to put a resistor here. There's a resistor here. What's happening? This is R. Can you see?
Yes, sir.
Yeah.
Got it, sir. Thank you, sir.
Yep.
Hello. Hello.
Hello. Yeah. Tell me.
Sir, hello.
Yes. Tell me.
Sir, in any current source we have designed, sir. Like we got like V by R equal to I naught, sir. For example, so this is independent of load, sir, right?
Yes. You're right.
So like it doesn't matter what is the load value, it will give the same current.
Yeah, as long as you don't saturate an op amp. Very good. That's a good idea, because if the load value is 1 ohm, 2 ohm, what will happen? There's a huge current flowing,
That's
and you
what
might even
was my
saturate the
question.
op amp.
Yes, sir.
So as long as the op amp works in the linear region, you can vary whatever load that you want. See, that is why all the resistors in op amp are in kilo ohms. They are not in mega ohms, or they're not in ohms. What is the reason they are not in ohms or they are not in mega ohms? If it is in ohms, there's a huge power dissipation, right? You can even the huge currents that are flowing, because 1 ohm is there, 1 volt, 1 ohm by 1 volt by 1 ohm. There's amperes of current flowing. So you cannot have smaller value of resistors. At the same time, you cannot have mega ohms and giga ohms. The reason is, if you have huge voltage, I'll tell you, you can have offset problems also, right? So always you should have kilo ohms. So the resistor will always have a range. That is why I took 1K to 5K. Are you getting?
Actually, I was thinking like instead of if we select V and R such that like we get a 1 ampere, and on that 2 terminals if we touch
But
our
who has to give that current, my dear? That current has to come from op amp also, no?
yes, sir.
Op amp will just get burnt. Op amp cannot give amperes of current.
Okay, sir, one
Our
more
op
thing.
amps are there, but they are not very popular, right? Normally op amps, they give, they can't give amperes of current.
All right, sir. So one more thing is there.
Yeah.
For example, if we are designing an op amp and it's giving 1 milliamp only, and like instead of R node, it's like ideally it is like we don't keep any resistor and it's infinite. Like 2 wires are placed nearby, the ground and the load other end. That is an infinite resistance, sir. So
Yes.
the voltage developed will be I naught into resistance, so that can be very large, right?
Voltage is the KVL in that loop, which will fall there.
The
If you open
voltage
circuit any
load
port,
is I
you
naught
have to
into
look at
RL.
other ends, no? What are the voltages in that loop? The algebraic sum of voltage in that loop is 0. So you have to calculate. You can't just open a port and say that here the voltage is going to be maximum. No. You have to look at the loop everywhere. You have to apply Kirchhoff. But without Kirchhoff, you cannot come to that conclusion.
Yeah, that was the doubting current source, sir.
Yeah.
Okay.
Yes.
Hello. Good evening, sir. Hello.
Yeah, next.
Hello.
Yeah, tell me.
Yeah, good evening, sir. Sir, can you please explain about the golden rules also?
Come again. What should I explain?
Golden rules, sir. Is that
Voltage?
golden rule, sir?
Voltage rule?
No, sir. Golden rules. Am I audible, sir?
Golden rule.
Yeah.
That is the golden rule is the virtual ground. Whenever you want to solve op amp problems, you have to follow 2 rules. The 2 rules are the voltage at plus terminal is always equal to voltage at minus whenever you give negative feedback. That is the first rule. Oh. Oh my God. Yeah, the golden rule here is whenever you give negative feedback, whatever the voltage that you apply here, the same voltage is going to get manifested here, right? So V plus or VP here, this voltage and this voltage, V plus and V minus, both are going to be same, right? Or if this is V in, this is going to be V. That is the first rule. The second rule is if you have a high input resistance in between the two terminals, I mean, which is generally the case, then op-amp draws no current. The current drawn by an op-amp is always zero because op-amp input resistance is zero. So with this rule, we have to do all the problems of op-amp provided there is negative feedback and the gain is very large. What is your doubt?
Okay, so is it like you have taken case 1 like G equal to 1 and case 2 G equal to 10, sir?
That
it will be
case,
like-
yeah. If gain is 1, then you cannot apply this rule. These two voltages will be diverged. For 1 volt, if the gain is 1, I have shown you that if this is 3 volt, this is 1 volt, there's a 2 volt difference. This is a huge value, right? So this is a useless op-amp. This is a useless op-amp. Op-amp gain will never be 1. Op-amp gain will never be 10. It will be 10 only in gate problems, right? Examiner wantedly says 10 so that you don't apply that rule. When you
Okay,
don't apply that, yeah.
So, okay, so if we make the problem, so we can take randomly, sir, like G equal to any value.
Your voice is not clear. If we take what?
If we solve any problem, sir, like suppose we are solving any problem, so we can take G equal to any value. And
Yeah, you want to solve any problem, you cannot always take V0 is A times of V1 minus V2.
Okay.
But you can take V1 equal to V2 only when A is infinite. A is infinite. The reason is, in this equation, see, forget about all the concept. Look at the math here. Math. V1 minus V2 is V0 by A. Can you see this?
Yes, sir.
If A is infinite, what will happen if A is infinite? It is 0.
Yes, sir.
So V1 minus V2 is 0. That means V1 equal to V2.
Yeah. Yes, sir.
Are you getting?
Yeah, I
So
got it, sir.
you can apply V1 equal to V2 only when, yeah, close. V1 equal to V2 only when A is infinite. Are you getting?
Yeah,
Never
I got
apply
it.
virtual short if A is finite.
Yeah, sure. I got it, sir. Thank you, sir.
Yeah, good. Yes, next. Next. Venkat, next student.
Good evening, sir.
Yeah, good evening.
Sir, can you go to 92F?
9.
92F.
Again this.
Sir, VD is 0 volt, na sir, here.
Yeah, V1 equal to V2. That means V1 minus V2 is VD.
Sir, but across the R, we have one voltage drop, na sir, by 8 volt.
Where is the voltage drop?
Across RL load.
Across the load. Here there is a voltage. Between the 2 points, there is a voltage.
So we can consider that Vx.
Yeah. What you said is actually correct. This plus terminal, there is a voltage. That's what you mean, right?
Yes, sir.
Yeah, you're right. The plus terminal is I0 into R. So the minus terminal will also be I0 into R.
Yes, sir.
So the plus terminal is I0. Minus terminal is also I0 into R.
बोलूं ना 5 मिनट.
Then the difference VD will always be.
Sir, another doubt, sir. Virtual short and virtual ground are same, na sir?
Yes. Same.
Sir, can you go to 33F?
33F. Yeah.
Sir, in all 33
This one?
Sir, in all the problems of virtual ground, you are considering non-inverting terminal voltage to the terminal. Sir, but here for non-inverting terminal, we have two resistors. Sir. The other
Yes.
resistor is connected to ground. Can't we assign inverting terminal, sir? If the op amp is ideal.
If the op amp is ideal.
For ideal op amp, virtual ground concept is applicable, na, sir?
For ideal op amp, virtual ground concept is applicable. We have applied here, no?
For non-inverting terminal, there are two resistors, na, sir? One resistor is connected to 0 volt.
Yeah. So
This can't be applied to the inverting terminal.
can't we apply to the inverting terminal?
Yes, sir.
Yeah, we have applied. No, V1 and V2 both are same. I
Yes.
Yeah, we have applied. We have applied. What you said is correct. This V1 and V2 we have applied in this here. Can you see this point? V1 equal to 1 equal to V2.
Yes, sir. Yes, sir. I will tell one problem. Can you solve the Miller effect, sir? Sir, negative feedback 3 kilo ohm. And for non-inverting terminal, we have dual and a current source.
You have a current source. Hello. Anybody else? Hello.
Hello, sir. Hello. Hello.
Yeah, tell me, I can hear you.
61F, sir.
61F. Is this?
Yes, sir. Sir, you told one short method by directly looking into the
No,
circuit.
not short method. There is a current IT into 2K. There's a voltage here, drop IT into 2K, yes or no? See, what is the resistor voltage across 2K? VT minus VX. Can you see?
Yes, sir, VT minus VX.
What is the voltage across 4K? VT minus VX. Can you see?
Yes, sir, same.
So both are having same voltage. But what is the drop here? IT into 2K. So VT minus VX is IT into 2K, no? So across 4K also IT into 2K will be the voltage. This is a voltage actually. This is a voltage. So what will be the current? IT into 2K by 4K. Let me draw it here. Yeah. See here. This is IT current. Am I right? 2K. This is IT into 2K is a voltage. Voltage is IT into 2K. Both are same. This 4K. Now this is IT. This is going to be IT into 2K by 4K, which is 0.5 IT. So this is 1.5 IT. Now Kirchhoff's law says that the algebraic sum of voltage in a loop is 0. So I took this loop and finished the problem. VT equal to IT into 2K plus 1.5 IT into 1K. So VT by IT is 3.5. Are you getting?
Yes, sir. Yes, sir.
Yeah.
Sir, 73F.
73. Yeah.
Sir, how you took that V0
Voltage division.
VN? Yes, sir.
You want me voltage division?
Yes, sir. Voltage division for VN, sir.
For VN, that's what the current flowing through R and the current flowing through C both are same, no? Yes or no?
Yes, sir.
That is why if the current is same, then you can apply. See, I'll show you like this. I'll take a fresh page and show you. Yeah. Now I have a voltage VN. Here there is R1 and here there is R2. All right. So what is V0? You already know the answer, no? What is V naught? This is a non-inverting amplifier. V naught is 1 plus R2 by R1 times of V. Do you remember this?
Sure.
Yeah. So you remember. Now, this Vn is this Vn. Let me solve this by another method. This is V naught. So I'm imagining that there is V naught. And whatever current flows through R1 is the same current flowing here. Do you remember?
Yes, sir.
Because op-amp draws no current. So this current and this current is also same, right? So I'm putting R2, I'm imagining R2 here, and there is R1 here, and there's a V in here. What mistake have I done now? So this V in by voltage division is going to be V naught into R1 by R2 plus R1. So your V naught is going to be 1 plus R2 by R1. Are you getting?
Yes, sir.
Yeah, good. See, when you do it with a different way, that's where a student will think. Otherwise, all the time entering, leaving, it's boring, no? Just a fancy way. Once I'll do by this, other time I'll do by that. Because student knows a different way of doing it, he can compare the answers. Are you getting? That is a beauty. You do by normal KCL, you do by current division formula, and then compare. You do by normal, you do by voltage division, compare like that. Okay?
Okay, sir.
Yeah, good.
89.
89. 89F. Yeah.
Sir, here at Vx we cannot apply voltage division rule, sir.
Where?
At Vx.
Yeah, you can apply provided same current flows through V, R, and RL. Whenever you are applying voltage division, remember the same current should flow through both the resistors. Okay.
Different.
This current through R and this current I naught, both are not same, no?
Yes, sir.
Yeah. Because some amount of current. Yeah, suppose you remove the whole op-amp. After Vx right side, the circuit is there, no? Complete circuit you remove, you apply voltage division, what is there? Then you can say Vx is V into RL by R plus RL. Doesn't matter.
Okay, sir.
Okay, good.
Thank you, sir.
Yeah. Next.
Hello.
Yeah.
Good evening, sir.
Good evening.
Sir, I have a doubt in yesterday's lecture. Sir, you taught in the topic negative feedback that as we increase the gain of the amplifier, the difference between the input decreases. Like
Yes.
it becomes negligible.
Yes.
Yes. So if almost it becomes the difference between the two inputs becomes negligible. So
Yes.
whatever signal we are providing, the information that is carried in that signal is almost attenuated, or you can say distorted. So then what is how is that signal again regained, or like the information stored in that signal
See, okay, this is a very valid point, what you have made.
Yes, sir.
See here, just imagine amplification is like magnifying a signal. Are you getting? So you have two mirrors with you. Through one mirror, you see there's a big signal. Through other mirror, you see it becomes very small. So I am giving 1 volt signal here to an amplifier. And this 1 volt signal, I'm applying. And what is the output? This is 9K, this is 1K. This output is 10 times of Vn. If this is 1 sin t, this is going to be 10. Okay.
Hello, sir.
Yeah.
Hello, sir.
And there is an error signal which is being generated by op-amp. Same thing. Like how op-amp generates this big signal, there is a small error signal also op-amp is generating with a small sine wave there in the middle. That is what it is amplifying. Op-amp is an error amplifier. Can you see?
Yes, sir.
So this Vd is actually Vin divided by 1 plus A beta. So if you give Vin, your Vd is this and your V0 is this. So now you tell me, what is op-amp amplifying? He is amplifying the attenuated version of your input first.
But sir,
This is Vin.
Hello, sir.
Yeah, tell me.
Sir, in some problems you considered output of the op-amp current due to output of the op-amp, sir. But in some cases you did not consider. When we have to consider and when we have to not to consider, sir.
You have to consider the current, provided the examiner wants you to find that current. Are you getting?
Sir,
Suppose
for example, open the sum in 92F page, sir.
92F. Yeah.
Here you didn't consider the output of the op-amp, sir. Means current.
Yes. When I have to, suppose I apply KCL at this point. Can you see this point?
Which point?
Then I have to apply, no? So I was very clever. I didn't touch, I was only looking at the voltages. What is my aim? My aim is not to find the op-amp current. My aim is to find I0.
Yes, sir.
So I very carefully moved all around this because the algebraic sum of voltage in a loop is 0. Suppose out of hastiness, if I find KCL at the output of an op-amp, then I'm gone. If you touch that node and apply KCL, then because you don't know the current through op-amp, no.
Sir, which node we have to don't touch, sir? I couldn't see that icon.
No, this here don't apply KCL. Always apply KCL here. Can you see this node?
Yes, sir.
Never apply here. If you apply here, you will find I0. If you want current, you can apply. What is that? Because your current is here, no op-amp current.
Sir, but here you took I plus and IR equal, na, sir?
See, the point is, let me tell you something. I have found it with a certain procedure, okay? Like another student was telling me, so for the same problem, I tried a different method. I got stuck. So when you try it with a different method, then you know where you will get stuck. Are you getting? So you do the same problem in the way you want and see what is the mistake you're going to do. That's the best way to learn how to solve networks. You just try with another method, but you still have to get the answer.
Sir, okay, then can you give me the conclusions where we can use and where we cannot use that?
Always apply KCL at the input node for voltages. And if you apply KCL at the output node, you will calculate the current through the op-amp. That's the conclusion.
Oh, okay, sir.
Okay.
Here all you considered only at the input node, so you didn't consider the output of the op-amp.
Yeah, I was just taking the drops, that's all. This is KVL. KVL deals with the drops, not with the currents.
Okay, sir.
Yeah.
Hello,
Thank you,
sir.
sir.
Yeah.
Hello, sir.
Yes.
Hello.
Sir, in this same question, sir, generally virtual short is applicable for negative feedback only, no, sir?
Yes.
So we don't need to check for this, sir?
No. There's no need for you to check. Because the examiner himself says it's an amplifier. Why you have to check?
Okay.
He's asking you to find the current, no?
Okay, sir.
Yeah, there's no need. This is negative. But how to check, you will have to wait. I will tell you how to check. I will check. I will tell you, I will give you different circuits and we will check whether it is negative or positive there. When I take a positive feedback, I will tell you. But right now, believe that these are all what feedback? Negative feedback. Can you see that the output is fed back to the minus terminal here? There's a buffer. The second
Yes, sir.
Yes or no?
Yes, sir.
Yeah. It's all negative feedback.
Okay, sir. Thank you.
Yeah.
Hello, sir.
Yes.
Sir, page number 65F.
65. Yeah, tell me.
Sir, 65. Sir, yesterday we derived Miller theorem using buffer, na?
Using buffer also? Okay.
Sir, there we use formula for internal resistance Z upon 1 plus A for negative gain.
This is negative gain only, no? Minus 2.
Sir, this is positive gain, na, sir?
No. This is negative. Input is given to minus terminal, no? V0 will be A times of V1 minus V2. V1 is grounded. V0 is minus 3V2.
Sir, in the next question.
See here. Please see here. This is V2, V0. What is V0 by V2? You tell me.
Sir, minus A.
This is a negative amp. Whenever there's a negative gain, there will be a positive answer, positive number.
Okay, sir. Then, sir, for in non-inverting amplifier, it will
not draw current, no? What you will calculate? Infinite.
Sir, but in the next problem,
I've connected another extra resistor through the feedback in the next problem.
Hello?
Hello?
Hello, sir.
Yeah.
Hello,
sir,
sir.
I have
Am I audible?
Yeah, yeah.
Am I audible?
Yes, yes.
Sir, page number 64F, sir.
Okay.
So here you made a statement regarding terminals, no, sir. Positive terminal and negative terminal.
Ah.
I couldn't get that statement, sir.
What statement did I make? The positive is grounded.
Yes, sir.
This.
No, sir. Not regarding this problem. A generalized statement like positive terminals and negative terminals regarding current and voltage.
I was telling that negative terminal are to simulate current. Positive terminals are to simulate voltage, I told. The reason is, see, generally from a signal source point of view, if the signal source sees a short circuit, then the signal is converted in current form. If the signal sees an open circuit, then the signal is converted in what form? Voltage form. Because in open circuit, voltage is manifested. Now, how do I know that this my signal is in current form at the inverting terminal? I'm also proving through resistance here. Can you see that my resistance becoming 0 here when the gain is infinite?
Yes, sir.
So this is virtual. Virtual means what? I don't know what is virtual. If my Hindi is good, it's kalpanik or something like that, right? It's not there, but its effect is there. Are you getting? You don't. It's not physically seen, but its effect is as if it is 0 ohms at the input. It's something like this. Can you see this diagram? It's something like this. There's virtually a short between the 2 points. Only when A is infinite.
Yes, sir.
Yeah. Only when A is infinite, there's a short, virtually short between the 2 terminals.
Okay, sir.
Sir?
Yeah.
So I have a question on finding a time constant. Today you were telling about gate question, that integrator, one capacitor, and with gain 10 to the power 3.
Yeah.
So there you have just taken that Rn side capacitance. We don't have to take the R outside.
We can take, but there are no resistors there, no? Resistor is 0. So tau is 0 there at the output side. What is said is correct. The total tau is input side capacitance plus output side, no?
Yes, sir.
Yeah, there is no tau there because there is no R there.
So one more time constant question. So it's something related to like network. It has a switch. So can you just solve it? So can you draw?
You want me to draw the diagram?
Yes.
Yeah, tell me.
So it has a voltage source of 0.5 volt.
Okay.
A resistor and an inductor is connected in series.
Okay.
And parallel to that inductor, there is a switch
Oh.
in series with resistor and 10 volt source.
All these switch close, open, T equal to 0. You will study networks class, no? You want me to?
So that's what I asked.
do
That
it,
will you?
Okay, tell me. One resistor, one inductor, one switch is there. Then.
So okay, sir, I'll leave it.
Okay, see, let me tell you something. So I have my number here. Some of you, if you wish, you can take. If you really feel that, sir, you're not, I mean, able to raise the hand. You can just post me. But please, I'm a married man, so you will have to wait, right? So don't think that the moment you give a question and the next answer, right, you don't get, right? But I will definitely answer. This is my phone number. Okay, so you can take this number. You can post your doubts in case if somebody doesn't get it.
So will you explain later relation between open loop gain and closed loop gain? So there was
A by 1 plus A beta, no? That's a closed loop gain. Open loop gain is A. Open loop gain is A. After feedback, closed loop gain is V0 by Vin is closed loop gain. Closed loop gain is V0 by Vin. It is A by 1 plus A beta. Open loop gain is V naught by VD, which is A. This is V naught, this is VD.
So there was a
Open loop
question
gain.
where open loop decreases by 10%, then what will be the change in
Yeah, that we
closed
will
loop?
solve in feedback amplifiers. Why do you worry? I will do it now.
So that's what I was.
I will do such problems in feedback amplifiers. If this decreases by 5%, 10%, what will happen?
Okay, so one op-amp question.
Yeah, if you will have to, you should, this is the formula which I will derive. DAF by AF is DA by A divided by 1 plus A beta. Okay, we'll do this slowly. We'll go slowly, okay?
Okay, so,
Don't
so
worry.
one op-amp question.
Yeah,
So there's an op-amp with current source of 0.1 milliampere
okay,
and a resistance connected in series.
okay,
It is in the inverting terminal.
okay,
And there is a feedback of 8 kilo.
okay.
And at the non-inverting terminal, there is a negative -2 voltage.
Yeah, this I will do in next class, okay? Orally, tell me the answer. Orally.
So I
This is
think
2 volt.
it was -30.
That is wrong. The book
That's-
which you have studied is
Yes,
giving
sir.
you a wrong. I know I'm not mentioning that book, but I don't know. I know from which book you have studied, and I know the problem because so many students have come and they say that, sir, we have done this problem. It's not there in the option. It's giving 30 answer.
Yes, yes.
So yeah. So please don't mention the book name. I know it. You know it, and
Yes, sir.
I will solve the problem in the next class. Please remind me,
Okay,
right? We can
So
only
last-
do it. This is true, so that is true. The same current will flow. So
Yes,
you get
yes.
the answer. It's very simple.
Yes,
right?
that's
And your
what
30 is
same
wrong.
question.
And your 30
Yes,
is
sir.
wrong.
Yes, yes.
Okay.
So one more last question. Determine minimum acceptable unity gain frequency for the circuit if response extend to at least 50 kilohertz. So
What?
what does this mean?
Nee, that is in frequency compensation topic. I will do in the class.
So all the questions are mixed, so I was a little confused.
Oh, all these problems we will do in the class. Why do you worry? Today
Hello.
we just introduced negative feedback. We have done differentiator, integrator. That's it. It's still a long way to go.
Hello.
Yeah.
Hello, sir. In page number 67F.
Yeah. 67. Yeah.
Sir, I need a clarification, sir. That if amplifier is, if the source is connected to the inverting terminal, we get the gain as negative, and if it is connected to the positive terminal, we get gain as positive. Is it right, sir?
You are absolutely right. Input is given to inverting, your gain is minus R2 by R1. There's always a phase shift. But if the
Okay.
input is given to non-inverting, you don't get phase. You're absolutely right.
Sir, in this, if the source is connected to the positive terminal, will I get the C equivalent as 1 minus A, sir?
No, the point is, if I give V in to the non-inverting, the current flowing through non-inverting is 0, so the source will see infinite. There is no question that the source is going to see infinite resistance through it. So, Acha, you want to calculate the time constant, not the input resistance. Yes.
Yes, sir.
For that, what you have to do is 1 plus R2 by R1 you have to do. By looking at the transfer function, then you can draw the plot, the Bode plot or whatever.
I didn't understand, sir.
See, if your input is at the non-inverting terminal, the only
Yes,
thing
sir.
what you cannot apply Miller's because
Okay.
here there is no current. What you can do is when the input is at non-inverting, this is V in. So this node is also at V in, and you can apply 1 plus R2 by R1. What I'm saying. See, that is why in filters we don't give at non-inverting, we give at inverting, so that we can simulate a different value of capacitance. That
Acha.
is not there, I'm saying.
Okay, so we get V naught is equals to 1 plus
1
R2 by
plus 1
R1.
by SC by R you will get. It depends what he asks.
Okay, sir.
Right now I cannot contemplate on this because filters are not designed like that.
Okay. So
Okay.
we cannot apply Miller's theorem to this, sir.
No. Miller's theorem is when you are seeing through that port. Suppose, see, I am applying Miller's theorem at node A, but my source is somewhere at node X, node B, node C. Then what is the point in applying Miller theorem? I'm saying.
Acha. Okay, sir.
So yeah, you have shifted that source to somewhere, and now for that capacitor you want to apply. Then what's the point? Because there's no current through non-inverting.
Okay. Yes, sir.
Yeah.
Thank you, sir.
Yeah. Next. Okay.
Hello, sir.
Yeah.
Sir, while calculating time constant, you told one point that looking from the capacitor, we will calculate that. Can you go to that page, please?
What is the page number?
Actually, I forgot.
Okay, then there are only two problems that I've done.
Yes.
Yeah, those two I will draw for you, no problem. Oh my God, what happened?
Hello.
Yeah, tell me.
Sir, can you explain about the Holland current source? I did not get the what's the negative resistance, and we are getting the output at gain is maximum. Can you explain once again, sir? I did not.
No. What is your doubt? I've explained so many times now. What is your doubt? Where is that you got stuck?
I stuck that I will get the negative resistance. Matlab,
Negative
parallel
resistance
with,
का मतलब ये है, see, the current is actually flowing in opposite direction. That's all. Why current will flow through feedback in opposite? Because output is 2 times of Vx and input is Vx. So V naught is at higher potential, Vx is at lower potential. So the actual current is flowing in this direction.
Hello.
Okay.
Sir, can you go to that page, please? That time constant while we are calculating, looking from the capacitor.
So that one, yeah. Why all these things are coming?
Close it or save it.
Save it.
Maybe something important.
So many things have come. Jao yaar. Yeah, wait. Yeah, can I draw it here? Can you see here?
Yeah. Yes.
Oh, it's gone. I don't know how it's gone. Yeah, I'll take a fresh page. See here.
Okay.
There's a capacitor here. Here you are calculating. That is one.
Okay.
And here you are calculating. From here you have to see these 2 points. And here there is virtual short for op-amp.
Okay.
So here it is seeing R1. Here it is seeing R2. What's the point?
So means every time if we calculate like for omega
Now
equal
is
to
always R Thevenin or R equivalent into C. R equivalent
Yes.
is the equivalent resistance seen by the capacitor.
Okay.
Yeah. This is logically I'm telling. If you have a doubt, element of doubt, you can find the transfer function.
No, without calculating transfer function that I'm asking. Like
That's what I'm saying. No, you remove the capacitor. See, for example, if I have a network like this, I told you there's a capacitor here, right?
Okay.
Now you have to calculate time constant. So you remove the capacitor, between the 2 points you will see. Suppose this is shorted here, right? So this is suppose 1K, 2K, 3K like that. So how will you calculate? When you see here, you have to reduce from this side. 1K parallel with 1K is 0.5. 0.5 is with 2. 2.5. 2.5 parallel with 3.
Okay. Just calculate R equivalent, then multiplied with C, then
See, that's
we'll
all.
calculate.
1K parallel 1K, 0.5 in series with 2, and then parallel with 3. That's it.
Okay. Got it.
Okay, good.
Sir, hello, sir.
Hello.
Yeah.
Yes, a virtual ground concept are used where the feedbacks are in negative, right? Given to in negative. Virtual ground concepts are used where feedbacks are given to negative, right?
Yes.
If feedbacks are given to in positive terminals and negative terminals both, then what up?
Yeah, then we have to calculate beta n and beta p. I'll tell you how to calculate beta n and beta p. If beta n is greater, all the amplifiers I have taken care that my beta n is more than beta p. That is why you are able to apply negative feedback. So we will do those problems when I take up positive feedback.
Okay, okay.
So don't worry about that.
Yes, sir.
We will calculate beta n, beta p. If beta n is greater than beta p, then only it is negative feedback. So your doubt is when both feedbacks are given, how do you judge whether it is negative feedback or positive? Am I right?
Yeah. Okay, sir. Thank
We
you.
do such problems in the class also. Okay.
Yes.
Hello, sir.
Yeah. Tell me.
Sir, can you open 89F slide?
89F. Yeah. This one.
Hi, sir. Sir, here how we got at RX, how you taken VX, sir?
No. Vx I don't know. Vx, how did I take? The voltage at non-inverting is Vx. Can you see my pen here?
Yes, sir.
Yeah, if this is Vx, this is also Vx.
Okay, sir.
Now you got it. Okay.
Sir, 82F.
82F. 82F, yeah.
Sir, can you please explain this? I didn't understand.
Yeah, see, I wanted to build a 1 milliampere current source, right? But we all know that you cannot get current without a voltage and a resistor.
Yes, sir.
But I want 1 milliampere. Suppose my R is 1K. Tell me if my R is 1K, what is 1K plus 1K? 2K. If my R is 2K, 2K plus 1K. So if I change R also, my total current should remain same. That is why it is current source. Now, what is current source? Though RL changes, their current should always remain same. That means this R should be much, much larger than RL. What if this R is almost equal to this value? If you keep changing RL, see, do you know that in a series circuit, same current will flow? Am I right?
Yes,
but
sir.
Who decides the current? Who decides the current in a series circuit? Tell me.
Source.
The one which is having large value.
Large resistance.
He decides the current. Other resistance. So this should be as large as possible. So that even if you change RL, the current will not change. That is the logic. But if you put R 1 mega ohm, your voltage should be 1000 volts, no?
Yes, sir.
So that is impossible to realize. That is why you have to study.
Sir,
Yeah.
Sir, why you have calculated V minimum here, sir? Okay, there R is 1 mega ohm.
R is 1 mega ohm. 1 milliampere, 1 milli into 1 mega ohm drop is 1000. From where that drop will come from source only, no?
Yes, sir.
So the source should at least be 1000. Okay, you put 1000 and calculate what is that. If V is 1000, R is 1 mega ohm, RL is 1K, then 1000 divided by 1 mega plus 1K is almost 0.9999 milli will get.
Okay, sir.
Okay, yeah.
Sir, one more. If gain is infinity, then current in op-amp will be 0, no, sir?
If gain is infinity, current flowing through op-amp, no. Current is only to do with infinite. Very good doubt you have asked. The current flowing through op-amp has got nothing to do with gain. It is something to do with the input resistance. If input resistance is infinite, then only you should take no current. Op-amp draws no current because the input resistance of op-amp is infinite. Are you getting it?
Yes, sir. Yes, sir.
If gain is infinite, then the voltage between the two terminals will also be very small.
Yes, sir.
Then what is the current? That small voltage divided by resistance. Yes or no?
Yes, sir.
Yeah, but we cannot rule out the resistance. That's what I mean. Because current is not just voltage. It is voltage by resistor. Current is 0, means resistance should be infinite.
Okay.
Okay? Yeah.
Yes, sir.
Okay, shall we stop? You have my phone number, right? Somebody who has not raised my hand, the hand and not able to reach me. You can post, I'll answer. Is there anybody else? Finally? Last candidate?
Hello, sir.
Yeah.
Sir, last problem, recognition of type of a filter.
Yes.
In the type of filter.
Yeah, tell me.
V0 out by V0 minus R2 by R1. I not understand all.
Acha, minus R2 by this one. This is the whole impedance. I'm putting it as Z. This is R2. This is an inverting amplifier, no?
Minus how would you?
Because this is an inverting. Acha, let me draw it like this. There is an inverting amplifier we have done in the class. This is R2. This is R1. Input is given to inverting terminal. Am I right?
Yes.
Yeah, this is virtually zero, no?
Oh.
Entering current equal to leaving. V in minus 0 by R1 equal to 0 minus V0 by R2. So your V0 is minus R2 by R1 times of V. Am I right?
Okay.
But in that problem, this R1 is nothing but Z. Z. What is Z? It is R1 plus a capacitor 1 by S2. Are you getting?
Yes, sir.
Yeah.
Okay.
Hello, sir.
Yes.
Sir, if gain is equal to 1000, then we can apply virtual short, sir.
No. Virtual
Only
short you can apply, but if the examiner wants the answer in terms of gain, that means you cannot say anything, right? See,
I mean, it would be
generally, please apply virtual ground only when the gain is infinite.
okay.
Infinite. Practically, what I'm saying is, if the gain is 1000 and above, right, or in lakhs, at least in lakhs, then 100% there will be virtual short. Almost. Are you getting? Because the error is very, very small.
Sir, if a gain is not given, then we'll take it as infinity only.
Yes. Very good. Gain is not given, you should always take it as infinite. If input resistance is not given, you should take infinite. If output resistance is not given, you should take 0.
Sir, one more. Sir, one more doubt. If virtual short is not applied, I mean, current in op-amp will not be taken 0, sir. I mean,
No.
every time.
If gain is less also, you can take current 0 because input resistance is not given, no?
Sir.
Yeah.
Okay, understood, sir. Thank you.
Yeah. Good.
Yes, sir.
Yeah. Anybody else? Is it okay? Shall we wind up for today? Yeah. Thank you.
Sir, class in the college. Venkat?
Sir, your screen sharing is on.
సార్ మీరు ఎగ్జిట్ అవ్వండి, క్లోజ్ చేయండి.